Tonight, we're going to confront something that feels almost like a contradiction. A world so massive, it should be impossible for a planet to exist at all. When astronomers first stumbled upon this object, they had to double-check, triple-check, and then check again, because the numbers just didn't add up. They were staring at something that was not just big, it was fundamentally wrong according to everything we thought we knew. This is not a simple story about size. This is a story about the blurry edge of what a planet even is, the battle between gravity and heat, and the discovery that our solar system is only one small, safe chapter in a much stranger book. By the end, you're going to understand why this specific object is rewriting the rules of planetary science, and why the biggest planet in the universe might be something entirely different than you imagine. Let's start with the obvious question. What exactly do we mean when we say biggest? Is it the most massive, the one with the most material crushed into its core? Or is it the largest in diameter, the one that would stretch the farthest from end to end? In our everyday world, these two measurements go hand in hand. A bigger rock weighs more. A larger building has more material. But in the universe of gas giants, those rules collapse into something far more counterintuitive. You can have a planet that is 9 times more massive than Jupiter, and it could be almost exactly the same size. You can have a planet that is the size of a massive hot air balloon, but barely heavier than a cork. The biggest planet in terms of sheer mass and the biggest planet in terms of sheer volume are often two completely different worlds. To understand why, we need to wrap our minds around the relationship between mass, gravity, and density. Imagine you have a balloon. You blow air into it, it gets bigger. But if you keep blowing, the rubber stretches, the pressure builds, and eventually it pops. A gas giant is like a balloon made of its own gravity. When you add more mass to a planet like Jupiter, you are adding more gravity. That gravity squeezes everything in the center harder. For a while, adding mass makes the planet larger. But there is a tipping point. Once a gas giant reaches about 3 times the mass of Jupiter, the extra gravity starts to win. The added mass no longer inflates the planet. Instead, it compresses the interior material into a denser, tighter ball. The planet starts to get smaller even as it gets heavier. This is the mass-radius paradox. It is the fundamental reason why the largest planet is a trick question. You have to decide what largest really means. Our own solar system gives us a starting point. Jupiter is the king here, roughly 86,881 miles across, more than 11 times wider than Earth. Its volume is staggering. You could jam over 1,300 Earths inside it, but its mass is only about 318 times Earth's. That is because Jupiter is mostly hydrogen and helium, the lightest elements known. It has an average density just slightly higher than water. Jupiter has already reached that tipping point. It is close to the maximum possible size for a gas giant. If you added a little more mass, it would actually start to shrink. So, if we are looking for the biggest planet in the universe by diameter, we are not looking for the heaviest. We are looking for something that has managed to puff itself up to weird proportions. Or we are looking at a very young world that hasn't had time to cool and contract. But mass is a different story. The record for mass belongs to objects that sit on a razor's edge. There is a hard limit in astronomy, the 13 Jupiter mass boundary. Below that number, an object is a planet. Above it, something fundamentally changes. At that point, the pressure and temperature at the core become high enough to ignite the fusion of deuterium, a heavy form of hydrogen. This is not the full hydrogen fusion that powers a star like the Sun. It is a lower energy, dirtier form of burning that fizzles out quickly. But it is enough. When an object starts fusing deuterium, it is no longer a planet. It becomes a brown dwarf, a failed star. It is a strange middle ground, too massive to be a planet, too light to be a true star. So, the absolute upper limit for a planet by mass is 13 Jupiters, at least by our current definition. The biggest planets in the universe, by mass, are the ones that dance right up to that line without crossing it. In 2011, astronomers discovered a planet that does exactly that. Its name is Arroxes 42b, and it is a monster. This object orbits a very young star about 460 light-years away, in the constellation of Ophiuchus. The star is only about 2 million years old. Our Sun is 4.6 billion years old. This system is barely out of its cosmic cradle. The planet is a brute. It has a mass estimated at roughly 9 times that of Jupiter. Let that sink in. 9 times the mass of the largest planet in our solar system. That puts it at nearly 3,000 times the mass of Earth. It is right on the edge of that brown dwarf threshold, a stone's throw away from being classified as a failed star. But here is where it gets truly bizarre. Arroxes 42b is not 9 times larger than Jupiter. It is only about 1.1 to 1.4 times wider. That compression effect is in hyperdrive. All that extra mass is not making the planet bigger. It is making it denser. The interior of this world is crushed under unimaginable pressure. The hydrogen at its core is likely compressed into a liquid, and deeper still, into a state of metallic hydrogen that conducts electricity. The average density of this planet is probably around 4 to 6 grams per cubic centimeter. That is denser than most rocks on Earth. It is a gas giant with the density of stone. This is the first lesson in finding the biggest planet. The most massive ones are often deceptively compact, hiding their true bulk under a shroud of extreme gravity. The strangeness of Arroxes 42b does not end with its density. It orbits its parent star at a staggering distance. We are talking about 157 astronomical units. 1 astronomical unit is the distance from Earth to the Sun. So, this planet is 157 times farther from its star than we are from ours. For a sense of scale, the Voyager 1 spacecraft, humanity's most distant probe, launched in 1977, is currently at about 160 astronomical units from the Sun. It took over 45 years of non-stop travel to get that far. This planet is at a similar distance from its star. The orbit is so vast that a single lap around the star takes about 2,000 Earth years. While our civilization has risen and fallen and built empires, this planet has barely moved a degree in its orbit. At that distance, the star provides almost no warmth. It appears as nothing more than a very bright, point-like light in the sky, barely distinguishable from any other star except for its intensity. And yet, Arroxes 42b is searingly hot. Its cloud top temperature is estimated at around 1,800 degrees Fahrenheit, hot enough to melt most metals. How is this possible without a nearby star to heat it? The answer lies in its youth. This planet is still radiating the heat of its own formation. 2 million years ago, this world was born from a collapsing cloud of gas and dust. As the material fell inward, gravity converted that kinetic energy into pure, raw heat. The core of the planet was heated to tens of thousands of degrees. It was glowing white-hot. It was, in effect, a tiny, short-lived star, powered by gravitational collapse rather than nuclear fusion. Over time, this heat leaks out into space. The planet cools. But for a massive object like this, the cooling is excruciatingly slow. The interior has a huge thermal mass. It is taking millions of years to bleed off that initial heat. So, at just 2 million years old, it is still a furnace, glowing brightly in the infrared, completely independent of its distant sun. This thermal glow is why we can see it at all. Rox's 42b was discovered via direct imaging. This is the most difficult way to find a planet. You are not looking for a shadow or a wobble. You are trying to take an actual photograph of a dim point of light next to a blinding star. It is like trying to photograph a firefly sitting on the edge of a lighthouse beacon from a mile away. Most planets fail this test. They are too close to their star, or too cold, or too small. But Rox's 42b has all the advantages. It is far from its star, young and hot, and the star itself is relatively faint for its type. Using the Keck telescopes in Hawaii with advanced adaptive optics, astronomers were able to block out the star's light and capture the faint infrared glow of the planet. They took a picture of it, confirmed its motion over several years, and proved it was gravitationally bound to the star. It was a real, solid, undeniable world. The existence of Rox's 42b immediately challenged our understanding of how planets form. The standard model, called core accretion, works like this. In the dusty disk around a young star, bits of rock and ice stick together, building up into a solid core. Once that core reaches about 10 or 15 Earth masses, its gravity becomes strong enough to pull in a thick envelope of hydrogen and helium gas. This is how we think Jupiter and Saturn formed. But there is a problem. Core accretion is slow, and it requires a lot of solid material close together. At 157 astronomical units from the star, the disk of dust and gas is incredibly thin and spread out. There simply is not enough material to build a massive core in the few million years the disk exists. The math does not work. Rox's 42b could not have formed this way. This forces astronomers to consider a second, more chaotic pathway: gravitational instability. In this model, the disk itself becomes unstable. If a region of the disk is massive enough and cold enough, its own gravity overwhelms the internal pressure of the gas. That region collapses directly into a clump, bypassing the slow core building entirely. This clump contracts into a planet or brown dwarf in a few thousand years, a cosmic blink of an eye. It is the same process by which stars form, just on a much smaller scale. If Rox's 42b formed this way, it is not a planet in the same sense as Jupiter. It is more of a failed binary star, a sibling of its star that simply did not gather enough mass to ignite. It is a planet by definition because it is below 13 Jupiter masses and it orbits a star. But its formation story is fundamentally different from everything in our own solar system. This leads us to the biggest planet candidates that have turned the universe into a laboratory of extremes. Let's shift focus from mass to volume. If you want the planet with the largest diameter, you are not looking for the most massive. You are looking for the puffiest, the most inflated balloon in the star system. Consider a world called TRAS 4b. This is a hot Jupiter, a gas giant that orbits incredibly close to its parent star. It is so close that it completes an orbit in just over 3 days. The star's radiation is intense. The planet's dayside temperature is around 2,700 degrees Fahrenheit. This heat is the key to its size. TRES-4b has roughly the same mass as Jupiter, maybe slightly less, but its diameter is an enormous 1.7 times larger than Jupiter. Its volume is nearly 5 times greater, and yet it weighs the same. The math gives us a density of about 0.2 grams per cubic centimeter. That is less than the density of cork. It is a planet with the consistency of a cappuccino foam. If you could find an ocean large enough, TRES-4b would float, bobbing on the surface like a giant beach ball. This extreme puffiness is a direct result of the heat. The intense radiation from the close star heats the planet's atmosphere, causing the gas molecules to move faster and spread out. The atmosphere expands into a vast, tenuous envelope. The planet's gravity, which is relatively weak for its size, cannot pull it back into a compact shape. But even this explanation has problems. Standard models predict that a hot Jupiter should be 10 to 20% larger than Jupiter, not 70% larger. TRES-4b is far puffier than theory allows. Something else is happening. Perhaps tidal forces from the star are heating the planet's interior, injecting extra energy. Perhaps the planet's magnetic field is interacting with the star's wind, creating additional inflation. Or perhaps the planet is simply young and has not had time to cool and shrink. Whatever the cause, TRES-4b shows us that you can build a planet that is massive in volume without being massive in weight. It is the biggest planet in terms of sheer physical presence, but it is practically empty. Now, what happens when you combine these two extremes? What if you take a supermassive planet like Rox's 42b and put it extremely close to its star? The result might be something like HAT-P32b, another contender for the title of largest diameter. This planet has a mass somewhere between Jupiter and Saturn, but it is even puffier than TRES-4b. Its radius is a staggering 2 times that of Jupiter. Its density is incredibly low. The heat from its star has inflated it to a near record size. But again, we run into the same mystery. The models cannot fully explain it. The observations push the limits of our understanding. We have to be careful here, because not everything that looks like a planet is one. The line between planet and brown dwarf is not just a number, it is a question of internal physics. The 13 Jupiter mass limit is a rule of thumb, but nature loves to blur lines. There are objects that might be right on the edge, where the exact mass is uncertain. A tiny error in measurement could mean the difference between being the most massive planet ever found and being a failed star. Take HD 10546b. This is a controversial object orbiting a young star about 335 light-years away. Estimates of its mass range wildly, from as low as 6 Jupiter masses to as high as 20. If it is on the high end, it is not a planet at all. It is a brown dwarf. The uncertainty comes from the difficulty of studying a planet that is still embedded in a thick disk of gas and dust. We might be seeing the glow of the planet itself, or we might be seeing light scattered off material in the disk. The debate is still active. This is the messy reality of astronomy. The boundaries are defined by us, but the universe does not care about our definitions. This brings us to a deeper question. Is size everything? The public loves records. They want to know the biggest, the heaviest, the most extreme. But science is not a competition. The value of these objects is not that they hold a title. It is that they break the mold. They reveal the hidden mechanisms of the cosmos. When we find a planet like Rox's 42b, we are not just adding a number to a catalog. We are testing the limits of planet formation theory. We are asking, how do you build such a massive object so far from its star? The answer, gravitational instability, implies that many of these massive worlds might not be planets in the traditional sense. They might be the runt siblings of binary star systems. This changes our entire picture of how planetary systems form. If gravitational instability is common, then the galaxy might be filled with objects that are neither stars nor planets in the way we think of them. It also forces us to reconsider our own solar system. For a long time, we assumed our system was the norm. Small rocky planets close in, gas giants far out, all in neat, almost circular orbits. This is not the norm. It is an anomaly. Most systems we have found look nothing like ours. They have hot Jupiters, super-Earths, and massive planets in bizarre, eccentric orbits. Our solar system might be the quiet, orderly exception in a galaxy of chaos. The existence of Rox's 42b and its extreme siblings tells us that in the universe, the strange is normal, and the normal is rare. We might ask, what is the absolute biggest planet possible? Is there a theoretical limit beyond which no planet can exist? Yes, but it is not as simple as the mass limit. The 13 Jupiter mass boundary is not a wall, it is a zone. An object right at 13 Jupiter masses is a brown dwarf, but it looks almost identical to a planet. Its atmosphere, its size, its behavior are indistinguishable from a super-Jupiter just below the line. The only difference is the invisible furnace of deuterium fusion in its core. So, the true limit for a planet is the deuterium burning threshold. But that threshold depends on composition. A planet made of pure hydrogen will start fusing at a lower mass than one with a higher fraction of heavier elements. Helium is a heavier element, and it changes the core pressure. So, the exact boundary can shift by a Jupiter mass or two, depending on what the planet is made of. There is also a limit to size. A planet cannot be infinitely large. Even if you pump it full of heat, there is a point where the atmosphere becomes so tenuous that it boils away into space. The escape velocity of the planet sets a hard cap. If the thermal velocity of the gas molecules at the top of the atmosphere exceeds the escape velocity, the planet loses its atmosphere entirely. This is what happened to a class of worlds we call Chthonian planets, the naked rocky cores of former gas giants. The biggest possible planet by diameter is a balancing act. It has to be massive enough to hold on to its gas, but heated enough to be puffy, but not so hot that the gas escapes. It is a narrow window. Finding these extreme objects is a way of mapping the boundaries of that window. Let's take a step back and look at the bigger picture. The search for the biggest planet is not a static hunt. It is a journey of discovery that has completely rewritten the textbooks in the last 30 years. Before 1995, we had no confirmed exoplanets around Sun-like stars. We had theories, but no data. We assumed other systems would look like our own. Then we found 51 Pegasi b, a gas giant zipping around its star every 4 days. It was impossible according to our models. It could not have formed there. It must have migrated inward. This discovery shattered the paradigm. Suddenly, the universe of planets was open to infinite possibilities. We found hot Jupiters, eccentric Jupiters, super-Earths, mini-Neptunes, and worlds that orbit binary stars. We found planets that orbit backwards relative to their star's rotation. We found planets with no stars at all, rogue worlds drifting through the void. And we found objects like Rox's 42b, so massive they blur the line between planet and star. Every discovery like this is a stress test for our theories. The theories are not wrong. They are incomplete. They were built on a sample size of 1, our own solar system. Now we have a sample size of thousands. We are in the process of building a new, universal theory of planet formation and evolution. The biggest planets are the most useful stress tests because they amplify the physics. The extreme gravity, the extreme heat, the extreme distances force our models to the breaking point. When a model breaks, we learn something new. Think about the future. The James Webb Space Telescope is already changing the game. It can look at planets like Rox's 42b in infrared light with unprecedented sensitivity. It can take a spectrum of its atmosphere, breaking down the light into a fingerprint of molecules. We can look for water, methane, carbon dioxide, and even complex organic compounds. We can measure the temperature at different layers of the atmosphere. We can detect the weather patterns on a world 460 light-years away. And the next generation of ground-based telescopes, the Extremely Large Telescope and the Giant Magellan Telescope, will have mirrors the size of a tennis court. They will be able to image planets directly with even greater clarity. They will find smaller, cooler, older planets. They will find planets that are currently invisible to us. In the next decade, we might find an object that is truly at the boundary. A world with a mass of 12.9 Jupiter masses, so close to the brown dwarf limit that the error bars overlap. We will have to argue whether it is the biggest planet ever found or the smallest brown dwarf. The debate will be fierce, and it will be productive. It will force us to refine our definitions and our understanding. And somewhere out there, there might be a world that is even more massive, a world that should have become a star but didn't, a world that is orbited by its own system of moons, some of which might be habitable. This brings us to a final, humbling thought. We have talked about Rox's 42b, TRES 4b, and the contenders for the crown. But the truth is, we do not know what the biggest planet in the universe is. We have only surveyed a tiny fraction of the galaxy, and a tiny fraction of the planets within that fraction. Our detection methods are biased. We are good at finding big planets close to their stars. We are terrible at finding planets far out, or planets around distant stars, or planets that are cold. The biggest planet in the entire universe might be out there right now, orbiting a star in a distant galaxy, completely undetectable by any technology we have. It might be so massive that it is on the verge of being a star itself. It might be a world of pure chaos, with storms the size of our planet and gravity that would crush you into a smear. We will never know. But that does not mean the search is pointless. The hunt is the point. Every new discovery, every new extreme is a piece of the puzzle. We are stepping out of our solar system for the first time, and we are finding that the universe is far stranger, far more diverse, and far more wonderful than we ever imagined. The biggest planet ever discovered is not just a number, it is a signpost. It marks the edge of our known territory. It tells us that the universe is a place of extremes and that our understanding is always provisional. Tomorrow, A new observation could break the record. A new theory could redefine what a planet is. The hunt for the biggest planet is a hunt for the limits of what is possible. And in that hunt, we find the true nature of our universe, a place of infinite variety, infinite mystery, and infinite wonder. That is the story of the biggest planet. And it is a story that is still being written. One light year, one telescope, one impossible world at a time. Consider this. Every time we think we have found the limit, nature throws us a curveball. We have objects that sit right on the 13 Jupiter mass boundary, like the candidate around the star HD 10546. The uncertainty in its mass is so large that we cannot say for sure whether it is a planet or a brown dwarf. But that uncertainty is itself a discovery. It tells us that the universe is not built around our labels. It is a continuous spectrum. On one end, you have Earth, a solid rock. On the other, you have the Sun, a blazing fusion engine. In between, you have gas giants, ice giants, sub-brown dwarfs, brown dwarfs, and everything in between. The categories we draw are lines in the sand. They are useful tools, but they are not laws of nature. The universe does not care if we call Rox's 42b a planet or a failed star. It exists, it orbits, it radiates heat. Our job is to understand its physics, not to force it into a box. This is where the future becomes truly exciting. We are building telescopes that will not just find more candidates, but will actually measure their masses with precision. The James Webb Space Telescope can do this. It can observe the subtle wobble of a star caused by a massive planet, even from a distance of hundreds of light years. It can also see the planet's own thermal glow. By combining these data, we can pin down the mass to within a few percent. For objects right at the boundary, that precision will be enough to decide. In the coming years, we will have a definitive list of the most massive planets, and we will know exactly where the line is drawn in reality, not just in theory. But the biggest planet is not just about mass. It is about size, and there, the record is even more precarious. The puffy planets like TRIAS 4b and HAT P32b are inflated by heat, but those planets orbit very close to their stars. What if we find a planet that is both massive and puffy? What if we find a world with 10 Jupiter masses and a diameter twice that of Jupiter? That would be a true monster. Could it exist? Theoretically, the compression effect should prevent it. A massive planet has stronger gravity, which pulls its atmosphere inward. But if the planet is also young and hot, the internal heat can counteract that gravity. A young massive planet could be both heavy and large. Rox's 42b is young and massive, but it is not hot enough to be puffy in the same way. Its temperature of 1,800 degrees Fahrenheit is not nearly as extreme as the 2,700 degrees of a close-in hot Jupiter. So, the puffy giants and the massive giants tend to be different populations. However, there is a class of objects that might combine both extremes, the so-called superpuffs. These are exoplanets with very low density, often found around young stars. They are not as massive as Rox's 42b, but they have radii much larger than Jupiter. For example, Kepler 51b and 51d are both about the size of Saturn, but with masses only a few times Earth. Their densities are lower than cotton candy. How do they form? That is another mystery. They might have extensive atmospheres of hydrogen and helium that are still fluffy from formation, or they might be dust-rich. with particles that scatter light in a way that makes them look bigger than they are. The superpuffs test our understanding of planetary atmospheres. They show that the relationship between size and mass is not simple. You cannot assume that a big planet is heavy. You have to measure both. And now, let's turn this back to our own solar system. We grew up thinking that Jupiter is the king. It is the biggest, the heaviest, the most dominant. But compared to these exoplanets, Jupiter is a moderate middleweight. It is not even close to the upper limit. Jupiter is about 0.1% the mass of the Sun. Rox's 42b is about 0.9% the mass of the Sun. That is still small compared to a star, but it is 9 times closer to the star threshold. In our solar system, the gap between Jupiter and the Sun is enormous. In other systems, that gap is much smaller. Some planets are almost stars. This changes how we think about the history of our own neighborhood. Could Jupiter have been bigger? Could it have grown into a brown dwarf if it had collected more gas? Probably not. The protoplanetary disk around our Sun was not massive enough. But the question remains, why did our system stop where it did? Why did we end up with a Jupiter and not a super Jupiter or a brown dwarf? The answer lies in the disk's mass and the timing of planet formation. Our system was not special, just a different set of initial conditions. Every extreme planet we find is a data point in a vast experiment. The universe is running trillions of planetary formation trials. We are the observers, collecting the results. And the results are telling us that the most common outcome might be something very different from our own system. The most common planet in the galaxy might be a super-Earth or a mini-Neptune. The most common giant planet might be a hot Jupiter or a puffy super-Jupiter. Our solar system might be an outlier, a quiet corner where the chaos settled down early. That is a humbling realization. We are not the center of the universe. We are not even the typical sample. So, what is the biggest planet ever discovered in the universe? The current answer, as of this recording, is Rox's 42b, with a mass about 9 times that of Jupiter. But that answer is provisional. Tomorrow, a new paper might announce a 10 Jupiter mass planet around a nearby star. Or the James Webb Telescope might image a 12 Jupiter mass object that is clearly a planet, not a brown dwarf. The record will keep being broken. That is the nature of exploration. We push the boundary, and the boundary moves. But the deeper answer is that the biggest planet is not a single object. It is a concept. It is the upper limit of planetary formation, the point where gravity wins and fusion begins. That limit is not a wall. It is a gradual transition. And we are mapping that transition, one discovery at a time. Every object we find near that limit teaches us about the internal physics of giant worlds. It teaches us about the conditions in the primeval disks where they were born. It teaches us about the final fate of massive planets, whether they will cool into lonely dark worlds or ignite into faint stars. We live in an age of exploration as profound as the age of sail, but we are sailing through the cosmos. Our ships are telescopes, our navigators are mathematicians, and our destination is knowledge. We have already discovered thousands of new worlds. The biggest planet is just the tip of the iceberg. Below it, there is a vast population of strange, extreme planets waiting to be found. Some of them might be more massive, some puffier, some hotter, some colder. The universe is not running out of surprises. And so, I leave you with this. The next time you look at the night sky, think about the unseen. The planets that are too dim, too far, too small for our telescopes. The rogue worlds drifting in the dark between stars. The massive objects that are on the verge of becoming stars. And the biggest planet of all, which might be out there right now, silently orbiting a distant sun, waiting for us to find it. We are the ones who will find it. We are the eyes of the human species. We are the curiosity that drives us onward. The biggest planet is not a destination, it is a direction, and we are heading that way. Thank you for joining me on this journey through the extremes of the universe. If you enjoyed this exploration, consider subscribing, because the universe is vast and there is always more to discover. Good night, and keep looking up. In the quiet hours of the night, when we look up at the stars, we see a tapestry of steady, distant lights. Each one is a sun, like our own, but they are not alone. Orbiting these distant suns are worlds so strange, so alien, that they challenge our very understanding of what a planet can be. For centuries, we knew only the 8 planets of our own solar system, familiar worlds of rock and gas, of ice and fire. But in the last few decades, our telescopes have opened a window onto a cosmos far more bizarre than we ever imagined. We have discovered planets where it rains molten glass, worlds darker than coal, and others that drift through the eternal night of space with no star to warm them. This is the story of the most bizarre exoplanets ever discovered, a journey into the extremes of planetary physics, where the laws of nature are tested to their breaking point. Let us begin by traveling some 750 light-years from Earth toward the constellation Draco. Here, a gas giant named TRES 2b orbits its star at a distance 30 times closer than Mercury is to our own Sun. But what makes this world truly remarkable is not its heat, nor its size, but its color, or rather, its complete and utter absence of color. TRES 2b is the darkest known exoplanet. It reflects less than 1% of the light that falls upon it. To put that in perspective, the Moon reflects about 12% of sunlight. Fresh asphalt reflects about 4%. This planet is blacker than coal, blacker than fresh acrylic paint, blacker than any object in our solar system. If you were to approach it in a spacecraft, your eyes would see nothing. The star behind it would be invisible. The planet itself would simply be a void, a hole in the fabric of space. This extreme darkness is not a trick of the eye. It is the result of a very specific chemical composition in its upper atmosphere. Because TRES 2b is so close to its star, its surface temperature soars to over 980 degrees Celsius, far above the melting point of lead. At these temperatures, the molecules that normally form reflective clouds, like the ammonia clouds that give Jupiter its bright bands, cannot exist. Instead, the atmosphere is saturated with vaporized sodium, potassium, and gaseous titanium oxide. These substances are remarkable absorbers of light. They trap almost every photon that enters the atmosphere, converting it into heat. The atmosphere becomes a dense, dark shroud, a one-way barrier for energy. The planet glows faintly in infrared, but in visible light, it is a ghost, a shadow world. If you were inside a spacecraft orbiting TRES 2b, you would experience a peculiar form of sensory deprivation. Your optical sensors would fail. Your navigation systems, which rely on star tracking, would become confused. The only way to know the planet was there would be through gravity. You would feel its pull long before you saw it, and if you descended into its atmosphere, the experience would be a nightmare of pressure and heat. The gravity is 1.5 times that of Jupiter. Your body would be crushed under its own weight. The gas density in the lower layers is so great that your shuttle would decelerate as if moving through thick syrup. The darkness would be absolute. There are no storms here, no lightning, no visible weather, just a dense, motionless mass of superheated gas and metallic vapors. TRAS-2b is a hell with a precise address. It is predictable, but it is no less terrifying. Now, imagine a world that has no address at all, a planet that has no star. This is the realm of rogue planets, worlds that have been ejected from their home systems, cast adrift into the cold void of interstellar space. For a long time, astronomers considered these objects theoretical curiosities, but they are real. One of the most famous is PSO J319.5222, a planet located about 80 light-years away in the direction of Capricorn. It is a gas giant, about 6 times the mass of Jupiter, and it is incredibly young, only 10 million years old. But the most astonishing thing about this world is its temperature. Despite traveling through space for millions of years, where background temperatures hover just a few degrees above absolute zero, its interior still burns at about 800 degrees Celsius. It has not had time to cool. PSO J319.522 is a planet without a sun, yet it is not cold. It radiates its own heat, a faint red glow in the infrared spectrum. If you could approach it in a spacecraft, your instruments would detect a massive gravitational body ahead, but your eyes would see nothing. The world is invisible. You would be falling into an unknown, dark gravity well. Only when you entered its atmosphere would you begin to perceive the reality of this orphan world. The weather here is not driven by sunlight. There are no day and night cycles. Instead, the entire atmosphere is churned by the planet's own internal heat. This is a world of eternal night, but it is not silent. Inside the atmosphere of PSO J319.522, the clouds are made not of water or ammonia, but of molten silicates and liquid iron. As you descend, you would hear a sound that cannot be reproduced on Earth. It is not the howling of wind. It is a continuous, overwhelming roar, like a million tiny hammers striking the hull of your spacecraft. It is the sound of droplets of liquid metal hitting metal. This is a world of rain made of incandescent shrapnel, and the deeper you go, the more intense it becomes. At a depth of about 100 miles, the pressure becomes so great that the gas transforms into a supercritical fluid, a state that is neither gas nor liquid, but something in between. Your spacecraft would no longer fall. It would sink. Every breath you took would feel as if your lungs were trying to move concrete. This is an environment that is fundamentally hostile to life as we know it. Yet it is a testament to the extreme diversity of planetary formation. From the dark mirror of TRAS-2b and the invisible fury of PSO J319.522, let us now turn to a world that is both beautiful and deadly in a completely different way. About 63 light-years away, in the constellation Vulpecula, lies HD 1189733b. This planet is a gas giant, slightly larger than Jupiter, and it orbits its star once every 2.5 days. It is tidally locked, meaning one side always faces its sun, a permanent day side. that burns at over 900 degrees Celsius. The night side, perpetually dark, is cooler, but still intensely hot. But what makes HD 1189733b infamous is its weather. This is a world where it rains glass, sideways. The upper atmosphere of HD 1189733b contains high concentrations of silicate particles. In the intense heat, about 900 degrees Celsius, these silicates evaporate, forming a vapor that rises into the upper atmosphere. As the vapor is carried by winds that blow at over 7,000 kilometers per hour to the cooler night side, it condenses into tiny droplets of liquid glass. But these are not the gentle droplets of a summer rain. The winds are so powerful that the glass droplets fly horizontally at supersonic speeds, like shards of shrapnel. They would shred any spacecraft attempting to enter the atmosphere. The planet appears a deep, rich blue, not because of water, but because the silicate particles scatter blue light in a way similar to Earth's sky. It is a beautiful, serene blue, but it is a blue of deadly glass. HD 1189733b also provides us with a vivid lesson in the atmosphere of extreme worlds. The star it orbits is an active red dwarf, which bombards the planet with high-energy radiation. This radiation strips away the upper atmosphere, creating a comet-like tail of escaping gas. Astronomers have observed this tail using spectroscopy, detecting the characteristic signatures of hydrogen, oxygen, and even carbon. The planet is slowly evaporating, losing about 100,000 tons of material every second. This is not an event that will destroy the planet anytime soon. It will take trillions of years for it to disappear. But it gives us a glimpse into the violent relationship between a star and its closest child. Let us travel further, to a world that defies our understanding of orbital mechanics. Just 1,400 light-years away, in the constellation Auriga, lies an unusual system named Kepler-16. What makes this system remarkable is that it contains a circumbinary planet, a planet that orbits not one, but two stars. This is the real-life version of the fictional world Tatooine from the Star Wars films. Kepler-16b is a cold gas giant about the size of Saturn, and it orbits two stars that themselves orbit each other every 41 days. The two stars are different. One is a K-dwarf, slightly smaller and cooler than our Sun, and the other is a red dwarf, much dimmer. The planet orbits the pair in a wide, stable orbit that takes about 229 days to complete. From the surface of Kepler-16b, if you could stand there, the view would be extraordinary. You would see two suns rising and setting, sometimes together, sometimes separately. The shadows would be multiplied. The daylight would vary in brightness as one star passed in front of the other, or the planet moved around its complex orbit. But Kepler-16b is likely too cold for life. Its surface temperature is estimated to be around -100 degrees Celsius, similar to Neptune's. It is a world of ice and frozen gas, but its existence proves that planetary systems can be far more complex than our own. A planet can have two mothers, two sources of light and warmth, and it is not alone. We now know of many circumbinary planets, each with its own unique orbital dance. From the double suns of Kepler-16, we travel to a world that is literally being torn apart. About 1,400 light-years away, in the constellation Leo, lies an exoplanet called WASP-12b. This is a gas giant of many extremes. It orbits its star in just over one Earth day. Its orbital distance is so close that the planet's atmosphere is heated to over 2,500 degrees Celsius on the day side. But the most dramatic aspect of WASP-12b is its shape. It is not spherical. The tidal forces from its star are so immense that the planet is stretched into an egg-like shape with its long axis pointed toward the star. The gravitational pull is so strong that it is actually pulling material from the planet's outer atmosphere, creating a stream of hot gas that spirals into the star. WASP-12b is being consumed alive. This process of tidal stripping is a slow-motion catastrophe. Astronomers have observed that the planet is losing mass at a rate of about 1 million tons per second. But because the planet is so large, about 1.4 times the mass of Jupiter, it can survive for millions of years. Eventually, however, its orbit will decay, and it will spiral into the star, ending in a final fiery merger. WASP-12b gives us a window into the end stages of planetary formation. It shows us that planets are not permanent. They can be destroyed by the very stars that gave them light. And it forces us to reconsider our own solar system. Could Earth ever suffer such a fate? The answer is no, because our orbit is stable and far away. But the universe is full of worlds that are not so lucky. Let us now consider a planet that might be the most valuable world in the galaxy. About 410 light-years from Earth, in the constellation Cancer, lies 55 Cancri. This is a super-Earth, a rocky world about 8 times the mass of our own planet, and it orbits its star in just 18 hours. It is incredibly close to its star, so its surface temperature averages around 2,000 degrees Celsius, hot enough to melt rock. But what makes 55 Cancri truly extraordinary is its composition. While Earth has a mantle rich in silicates, 55 Cancri appears to be rich in carbon. In fact, its carbon content may be so high that the planet is essentially a giant diamond. The idea is not as fanciful as it sounds. The planetary system of 55 Cancri is known to be carbon-rich. The star itself has a higher carbon-to-oxygen ratio than our Sun. The planets formed from this material, and if the ratio is right, a large fraction of the planet's mass could be composed of carbon in the form of graphite and diamond. Under the immense pressures of a planet's interior, graphite would transform into diamond. The result would be a world with a crust of graphite and a deep mantle of diamond, perhaps a layer hundreds of kilometers thick. The planet's surface, however, would not be a gleaming gemstone. It would be a lava world, covered in oceans of molten rock, with an atmosphere of vaporized carbon monoxide and nitrogen. But deep beneath that fiery surface, if you could somehow reach the interior, you would find a treasure that would beggar all the wealth of Earth. But is it really diamond? The answer is complicated. The planet's exact composition is still unknown. It might be a water world with a steam atmosphere, or it might indeed be carbon-rich. The uncertainty is part of the beauty of exoplanet science. We are still learning to read the stories written in the light of distant stars. 55. Cancri reminds us that the variety of worlds is limited only by the chemistry of their birth. From the diamond planet, we travel to a world that is perhaps the most hellish of all. About 65 light-years away, in the constellation Hercules, lies an exoplanet named Kepler-10b. This was the first confirmed rocky planet discovered outside our solar system. It is a small world, about 1.4 times the diameter of Earth, and about 4.6 times its mass. It orbits its star in just 0.84 days, closer than any planet in our solar system. Its surface temperature on the day side is estimated to be over 1,600 degrees Celsius, hot enough to melt iron. And indeed, the surface of Kepler 10b is likely covered in vast lakes and oceans of molten lava, glowing a dull red. The night side is cooler, but still hot enough to keep rock in a liquid state. As the planet rotates, the extreme temperature difference between day and night likely drives colossal winds that whip molten rock across the surface. The planet's tenuous atmosphere, if it has one, would consist of vaporized rock. This is a world where the rock itself is a weather system. Kepler 10b represents a class of exoplanets known as lava worlds. They are common around red dwarf stars, where planets can form extremely close in, and they challenge our imagination of what a solid surface can be like. If you could stand on Kepler 10b, you would be standing on a surface that is constantly melting and reforming, a place where the ground is never still. Let us now consider a planet that seems to break the rules of chemistry. About 30 light-years away, in the constellation Leo, lies an exoplanet called Gliese 436b. This is a Neptune-sized world, about 22 times the mass of Earth. It orbits its cool red dwarf star once every 2.6 days. The planet's surface temperature is about 440 degrees Celsius. That is hot enough to bake a pizza. And yet the planet is thought to be composed largely of water. How can water exist at such high temperatures? The answer is pressure. The immense gravity of Gliese 436b compresses its atmosphere to such a degree that water remains in a solid state even at hundreds of degrees Celsius. This is a form of ice that we do not have on Earth, hot ice, or ice 7, a crystalline form of water that exists only under extreme pressure. So, the surface of Gliese 436b is not a liquid ocean nor a gas. It is a layer of hot, solid ice. Above this, the atmosphere is thick with steam and hydrogen. It is a world of burning ice, a contradiction in terms. This teaches us that the familiar states of matter, solid, liquid, gas, are not absolute. Pressure can change everything. Water can be ice at a temperature hotter than boiling if the weight above is heavy enough. Gliese 436b is a world where the ordinary rules of our kitchen are rewritten by the cosmos. From the burning ice of Gliese 436b, we travel to another extreme, a world where the sky itself is a mystery. In the constellation Pegasus, about 437 light-years away, lies an exoplanet named HD 209458b, also known as Osiris. This was the first exoplanet discovered to have an atmosphere. It is a hot Jupiter, a gas giant orbiting very close to its star. But what makes Osiris famous is its evaporating atmosphere. The planet's outer layers are being blasted away by the star's radiation, creating a huge comet-like tail of hydrogen, oxygen, and carbon. The tail is so large that it extends for millions of kilometers. The planet is slowly losing its atmosphere, a process that will eventually leave behind only a dense core. Osiris is also one of the first exoplanets where we directly measured the composition of its atmosphere. Using spectroscopy, astronomers detected sodium, hydrogen, and even water vapor. This was a breakthrough moment in exoplanet science. It showed that we can study the chemical makeup of distant worlds, even though we cannot visit them. Osiris's atmosphere is also known for its extreme winds, which may reach speeds of several thousand kilometers per hour. The planet is tidally locked, so one side always faces the star. The day side is scorching, the night side is cooler, and the boundary between them is a region of ferocious storms. Let us now consider an exoplanet that defies our expectations of planetary orbits. About 1,200 light-years away, in the constellation Lyra, lies an exoplanet named Kepler 7b. This is a gas giant, about half the mass of Jupiter but 1.5 times its size. It is a very puffy planet with an extremely low density. It is so light that it would float on water if you could find a bathtub large enough. But more interesting than its density is its orbit. Kepler 7b orbits its star in just less than 5 days, which is typical for a hot Jupiter. But what surprised astronomers was that its atmosphere appears to be full of reflective clouds. This was discovered by measuring the amount of starlight that the planet reflects. While most hot Jupiters are dark, Kepler 7b is bright. Its clouds are likely made of silicates, but they are not the deadly glass of HD 1189733b. They are more like high-altitude haze, reflecting sunlight back into space. This discovery challenges our understanding of cloud formation on exoplanets. It shows that even in the extreme heat of a close-in orbit, clouds can form. And these clouds can drastically affect the planet's temperature and appearance. Kepler 7b is a reminder that the universe is full of surprises. Every new observation forces us to revise our models. From the cloudy world of Kepler 7b, we travel to a planet that might have a carbon-based atmosphere. About 200 light-years away, in the constellation Eridanus, lies an exoplanet named GJ1214b. This is a super-Earth, about 6.5 times the mass of our planet. It orbits a red dwarf star every 1.6 days. It is too hot for life, but what makes it interesting is its atmosphere. Observations suggest that GJ1214b has a thick, hazy atmosphere, possibly rich in water vapor or methane. The planet may be a water world, covered in a deep ocean with a dense steam atmosphere. Or it could be a world with a high-pressure atmosphere of carbon dioxide and nitrogen. The data are still ambiguous. GJ1214b is a reminder that we are still in the early days of exoplanet characterization. We can see that these worlds exist, but their true natures often remain hidden. Let us now return to the idea of rogue planets. PSO J317.5-22 is not alone. In fact, astronomers have discovered dozens of rogue planets, and there may be billions in our galaxy alone. Some of these worlds may be Earth-sized. Imagine a rocky planet, cold and dark, drifting through space for billions of years. Its surface would be frozen, a deep ocean of ice. But if it has a thick atmosphere of hydrogen, it might trap enough heat to keep a liquid water ocean beneath the ice. Such a world could be habitable. In fact, some scientists have speculated that life could exist on rogue planets, using chemical energy from hydrothermal vents or from the planet's own internal heat. This is not science fiction. It is a serious scientific hypothesis. The universe may be teeming with dark, hidden worlds, drifting silently in the void. To understand the full range of bizarre exoplanets, we must also consider the extremes of planetary density. In the constellation Monoceros, about 3,800 light-years away, lies an exoplanet named Kepler 51b. This is a gas giant, but it is extremely low density. In fact, it is so puffy that its density is lower than that of cotton candy. It is about the size of Jupiter, but its mass is only about that of Saturn. How can a planet be so light? The answer is its youth. Kepler 51b is only about 100 million years old, and it is still contracting from its formation. Its atmosphere is hot and extended, making it appear much larger than it really is. As it ages, it will shrink and become denser. Kepler 51b gives us a snapshot of planetary evolution, a glimpse of what our own Jupiter might have looked like billions of years ago. From the fluffy world, we travel to a planet of extreme density. About 400 light-years away, in the constellation Serpens, lies an exoplanet named Corot 7b. This was one of the first rocky exoplanets discovered, and it is a lava world similar to Kepler 10b. But Corot 7b has a fascinating story. It orbits its star in just 20 hours. The day side is a molten ocean of rock, while the night side might be covered in solid rock. The heat is so intense that rocks vaporize on the day side and then condense as rock clouds on the night side. The result is a planet with a rock cycle that includes rock rain and rock snow. This is a world where geology and meteorology are the same thing. The discovery of such worlds has profound implications for our understanding of planetary formation. We used to think that planets formed in ordered zones. Rocky planets close in, gas giants farther out. But the discovery of hot Jupiters and lava worlds upended that idea. It suggests that planets can migrate inward, scattering like billiard balls in the chaos of a forming solar system. This process of migration can produce worlds in places we never expected. Let us now think about the most extreme planet ever discovered, perhaps the most extreme in terms of heat. About 2,500 light-years away, in the constellation Cygnus, lies an exoplanet named Kepler 70b. This is a planet that orbits a star that has already gone through the red giant phase. The star shrank back into a white dwarf. During the red giant phase, the star would have expanded to engulf its inner planets, turning them into cinders. But Kepler 70b somehow survived. It now orbits the white dwarf every 5.76 hours. Its surface temperature is estimated to be over 7,000 degrees Celsius. That is hotter than the surface of the Sun. This planet is literally a ball of vaporized rock, a world that is more like a glowing ember than a solid planet. How could such a world exist? The answer is that the planet itself is only about the size of Earth, but its orbit is so close that the white dwarf's intense gravity is tearing it apart. It is a world that is dying, slowly being consumed by the star's gravity. Kepler 70b is a testament to the violence of stellar evolution. It shows that even after a star's death, its planets can still suffer. From the furnace of Kepler 70b, we turn to a world that is the opposite in temperature. About 600 light-years away, in the constellation Eridanus, lies an exoplanet named VHS 1256b. This is a young gas giant, about 11 times the mass of Jupiter. It orbits a pair of red dwarf stars at a distance of about 100 astronomical units, far beyond the distance of Pluto from our Sun. At that distance, the starlight is dim. The planet's temperature is about 600 degrees Celsius, which is actually quite cool for a gas giant. But what makes VHS 1256b remarkable is its atmosphere. Observations with the James Webb Space Telescope have revealed a complex atmosphere full of clouds and hazes, with signs of water, methane, carbon dioxide, and even sodium. The clouds are likely made of silicates and iron, similar to the rogue planet PSO J311.5-22. But VHS 1256b has a star to illuminate its clouds, making it a beautiful object to study. This planet is a bridge between the gas giants of our solar system and the directly imaged exoplanets of other systems. It shows us the subtlety of planetary atmospheres. Every molecule tells a story. The presence of methane, for example, tells us about the chemistry of the planet's interior. The presence of water tells us about the planet's formation. With every spectrum we capture, we learn a little more about the diversity of worlds. We must also consider the planets that are not just bizarre in themselves, but in their systems. For instance, the TRAPPIST-1 system, about 40 light-years away, contains 7 Earth-sized planets orbiting an ultra-cool red dwarf star. 3 of these planets are in the habitable zone, where liquid water could exist on the surface. But the star itself is remarkable. It is so small and cool that it emits most of its energy in the infrared. The planets are so close to the star that they are tidally locked. Their surfaces are likely different from Earth in ways we can only imagine. They could have global oceans, or they could be dry deserts. The atmosphere of TRAPPIST-1e, one of the habitable zone planets, might be rich in oxygen or carbon dioxide. The James Webb Space Telescope is now studying these planets, searching for signs of life. The TRAPPIST-1 system is a microcosm of planetary science. It shows how common small rocky planets are around the most abundant stars in the galaxy. Red dwarfs make up about 75% of all stars. If a fraction of their planets are habitable, then the number of potentially life-bearing worlds in the Milky Way could be in the billions. This is a stunning realization. We are not alone in the universe in terms of numbers. The question is whether any of these worlds are actually alive. From the habitable zone of a red dwarf, we travel to a world that has 2 suns, but also 2 very different faces. In the constellation Scorpius, about 470 light-years away, lies an exoplanet named HD 20782b. This planet has the most eccentric orbit of any known exoplanet. Its orbit is shaped like a very stretched ellipse. At its closest, it comes within 0.06 astronomical units of its star, closer than Mercury. At its farthest, it swings out to 2.6 astronomical units, beyond the orbit of Mars. This wild orbit means that the planet experiences extreme seasons. When it swings close, its atmosphere is heated to thousands of degrees. When it swings away, it cools down. The planet is likely a gas giant, and its atmosphere is subjected to violent thermal shocks every 180 days. This is a world of extremes, a cosmic roller coaster. How did such an orbit form? It is likely that HD 20782b was scattered by a gravitational interaction with another planet or star. The system's history is chaotic. This exoplanet is a reminder that planetary orbits are not always gentle. Sometimes they are the result of violence and instability. Let us now consider a planet that is the opposite of dark. In the constellation Ursa Major, about 180 light-years away, lies an exoplanet named 55 Cancri d. This is a gas giant, about 4 times the mass of Jupiter, and it orbits its star in about 14.5 years. It is not a hot Jupiter. It is a cold Jupiter, similar to our own, but with a twist. The star, 55 Cancri A, is a yellow dwarf very similar to our Sun. The system also contains the super-Earth 55 Cancri E, which we discussed earlier. But the outer planet, 55 Cancri D, is remarkable because it may have a ring system. The planet's light curve shows hints of possible rings, similar to Saturn's. If this is true, then the rings of 55 Cancri D would be visible from Earth with a powerful telescope. It is a beautiful, serene world, a peaceful giant in a system that also contains a lava world. The diversity within a single system is astonishing. We have a star, a hot lava world, and a cold ringed gas giant. This variety is likely the rule, not the exception. Every planetary system is a unique ecosystem of worlds. In our journey through the bizarre exoplanets, we have encountered darkness and light, fire and ice, chaos and stability. But one of the most profound discoveries is that of exoplanets that challenge our definition of a planet itself. Consider a world like Kelt 9b. This planet orbits a star that is twice as hot as our Sun. The star, Kelty 9, is a blue supergiant with a surface temperature of over 10,000 degrees Celsius. The planet orbits it every 1.5 days. The day side of Kelty 9b is heated to over 4,300 degrees Celsius. That is hot enough to break apart molecules. In fact, the molecules in its atmosphere are dissociated into atoms. Hydrogen atoms are ripped apart into protons and electrons, creating a layer of ionized gas. The planet blazes with ultraviolet and blue light. It is a world that is more like a star than a planet. It is a reminder that the boundary between star and planet is fuzzy. At these temperatures, the planet's atmosphere is constantly boiling away. Kelty 9b is a comet-like world, streaming material into space. It is a world that is actively dying, but in a way that is visually spectacular. From a distance, it would appear as a brilliant blue dot, surrounded by a glowing nebula of its own disintegrating atmosphere. From the extremes of heat, we return to the cold. About 200 light-years away in the constellation Lyra lies an exoplanet named Kepler 421b. This is a gas giant about the size of Uranus, and it orbits its star once every 704 days. That is a long year. But what makes Kepler 421b interesting is that it orbits within the snow line of its star. The snow line is the distance from a star where water ice can form. For our solar system, the snow line is about 2.7 astronomical units between the orbits of Mars and Jupiter. For Kepler 421's star, the snow line is farther out. Kepler 421b is a cold world, with temperatures below -200 degrees Celsius. Its atmosphere is likely filled with clouds of water ice and methane ice. It is a world of eternal snow, a frozen giant. But even in the cold, there is beauty. The reflected light from the star would make the planet glow like a white pearl. It is a serene, silent world, a reminder that the universe also includes quiet, frozen places. We have now covered a wide range of bizarre exoplanets, from the darkest to the brightest, from the hottest to the coldest, from the most massive to the least dense. But behind each of these worlds lies a story of discovery. The first exoplanet was discovered in 1992. Since then, we have found over 5,000 confirmed exoplanets, with thousands more candidates. And we are only scratching the surface. The Kepler Space Telescope, the Transiting Exoplanet Survey Satellite, and the James Webb Space Telescope are revolutionizing our understanding. Every new observation brings new surprises. One of the most recent and exciting discoveries is that of exoplanets in the habitable zone of red dwarf stars. But these planets face a problem. Red dwarfs are known for their intense flares, which can blast a planet's atmosphere away. However, recent studies suggest that some atmospheres can survive. The planet Proxima Centauri b, only 4.2 light-years away, is a rocky world in the habitable zone of the nearest star to our solar system. It is a tempting target for future telescopes. Could it harbor life? We do not know, but it is a world that we may one day study in detail. Another recent discovery is that of exoplanets made entirely of ice. There are worlds that are essentially giant balls of ice and rock with no significant atmosphere. They are like the icy moons of our solar system, but on a planetary scale. These worlds are cold, dark, and silent, but they are all common. The universe is full of such frozen spheres. As we reflect on these bizarre exoplanets, we must also reflect on our own place in the cosmos. Our Earth is a tiny oasis in a vast desert of extremes. Every bizarre world we discover reminds us of how rare and precious our own planet is. The gentle blue sky, the liquid water, the stable orbit, these are not the norm. They are a cosmic accident, a gift of nature. And yet, in the strangeness of these other worlds, we see a reflection of the universe's creativity. The laws of physics are the same everywhere, but they produce an infinite variety of outcomes. TARI S2b, the dark world, shows us that even absence of light can be a property. PSO J3118.522, the rogue planet, shows us that a world can survive without a star. HD 1897333b, the glass rain world, shows us that a color can be deceptive. Kepler 16b, the double sunset world, shows us that the sky can have two suns. 55 Cancri E, the diamond planet, shows us that wealth can be hiding in the heavens. Gliese 436b, the burning ice world, shows us that the familiar can become alien under pressure. And beyond all these, there are worlds we have yet to discover. The universe is vast, and our explorations have only just begun. There are likely planets made of carbon, planets made of iron, planets that are essentially balls of foam, planets with rings that stretch across the sky, planets where the atmosphere is so thick that the surface is an ocean of compressed gas. There are planets that orbit black holes, planets that are ejected from their galaxies, planets that are older than the Earth itself. The story of exoplanets is the story of the cosmos itself. It is a story of formation, destruction, and transformation. Every world has a birth, a life, and a death. Some die spectacularly, consumed by their stars. Others drift silently into the dark, never to be seen again. Some remain stellar for billions of years, providing a home for life, if life arises. And we, the observers, are part of this story. We are made of the same stardust that formed these worlds. The atoms in our bodies were forged in the hearts of ancient stars. Our curiosity is a product of the universe's own self-awareness. When we wonder about these bizarre exoplanets, we are wondering about our own origins. In the quiet of the night, as you drift into sleep, remember that the stars above are not just points of light. They are suns with families, and those families are full of strange children. The universe is more fantastic than we can imagine. It is a place of endless wonder, a canvas painted with worlds beyond our wildest dreams. And so, as we close this journey through the most bizarre exoplanets ever discovered, let us feel a sense of peace. The cosmos is vast, it is strange, and it is also beautiful. In its extremes, we see the power of nature.
This is one of the most hostile places known to us, where temperatures are measured in millions, and magnetic forces twist and break with unimaginable power. And yet, in this realm of extreme phenomena, a lone spacecraft is rewriting our understanding of the star that gives us life. Exceeding speeds of any human-made object, it flies closer to the sun than anything in history, enduring conditions that melt solid metal. But it's not just proximity or speed that makes this mission remarkable. What makes it outstanding are the secrets the spacecraft is uncovering, the hidden mechanisms that might explain why the sun's outer atmosphere defies logic, becoming hotter the farther it is from the star's core. Throughout its journey, the probe has also uncovered new mysteries about Earth's closest neighbor, peering through Venus's thick clouds to capture its surface. These unexpected discoveries reveal not only the structure of distant worlds, but also clues that shape our entire system. This is the story of how humankind touched the sun. What does it take to send a spacecraft closer to the sun than anything humanity has ever built? The Parker Solar Probe is a mission that represents the pinnacle of solar exploration and the study of the physics that defines our star. Named after Eugene Parker, the visionary physicist who predicted the existence of the solar wind in the 1950s, this probe achieved what was once thought impossible: entering the sun's outer atmosphere and withstanding its brutal conditions. The sun emits a constant stream of charged particles known as the solar wind that travels through space and interacts with planets, influencing phenomena like Earth's auroras. Parker's theories revolutionized our understanding of solar activity, but confirming these ideas required more than telescopes. It demanded a daring journey to the heart of the solar system. What makes this mission groundbreaking is not only its proximity to the sun, but also the record-breaking speeds it has achieved. At its peak speed, the probe reached 430,000 miles per hour, nearly 0.061% of the speed of light. For reference, at this speed, you could travel from New York to Tokyo in under a minute. Such speed is no accident. The sun's immense gravitational field accelerates the probe as it approaches, using gravity-assist maneuvers near Venus. Speed here is not just a statistic, but a necessity. Moving so quickly allows the spacecraft to outrun the sun's intense heat for brief intervals, while collecting high-resolution data. The key to the probe's survival lies in its revolutionary design. At the forefront is a thermal shield made of carbon composite material, capable of withstanding the searing heat of our star. Behind this protective barrier lies an array of sensitive instruments measuring magnetic fields, particle flows, and the sun's mysterious heating mechanisms. Thanks to these innovations, we can finally explore why the solar corona is millions of degrees hotter than its surface, and how solar storms affect space weather. Understanding these phenomena is essential not only for satisfying scientific curiosity, but also for protecting our technology-dependent society from disruptions caused by such powerful energy. It's become clear to many people that this spacecraft is not just another probe, but a technological marvel. The Parker Solar Probe was developed as part of NASA's Living with a Star program to study aspects of the Sun-Earth system that directly impact life and society. The Living with a Star program is managed by Goddard Space Flight Center in Greenbelt, Maryland, for NASA's Science Mission Directorate in Washington. The Applied Physics Laboratory designed, built, and operates the spacecraft and manages the mission for NASA. Its mission is projected to last 7 years, during which it will complete 24 elliptical orbits around the Sun, each bringing it closer to the blazing star. The longevity of the probe in such a harsh environment is made possible by its advanced thermal shield. The 4.5-inch thick carbon composite shield allows the spacecraft to withstand temperatures exceeding 2,500 degrees Fahrenheit, while keeping its instruments at a comfortable 85 degrees Fahrenheit. This combination of durability and complexity ensures that the Parker Solar Probe can survive close encounters with the Sun while maintaining precision in its measurements. One of the probe's primary objectives is studying the solar wind, a stream of charged particles emanating from the solar corona and influencing planetary environments across the solar system. By flying directly through this wind, the spacecraft measures its speed, composition, and magnetic structure, providing unprecedented insight into its dynamics. Another enduring mystery is the phenomena of coronal heating. Despite being farther from the Sun's core, the corona is hundreds of times hotter than the surface. The probe investigates this paradoxical phenomena, studying switchback, sudden reversals in the Sun's magnetic field that may play a role in transferring energy to the corona. We'll circle back to that in a few minutes. Additionally, the probe studies solar flares, explosive bursts of energy that emit radiation across the electromagnetic spectrum. By analyzing these events up close, the spacecraft helps scientists understand how flares develop and how they impact space weather, which can disrupt satellites and power grids on Earth. Moving at nearly 430,000 miles per hour, the Parker Solar Probe has redefined the concept of speed in space exploration. To put this into perspective, this velocity is sufficient to circle the Earth more than 17 times in a single hour. As mentioned, such speed is a critical characteristic that enables the spacecraft to fulfill its mission. The probe's extraordinary speed is largely a result of carefully planned gravitational assists, particularly from Venus. With each flyby, the spacecraft leverages the planet's momentum to alter its trajectory and accelerate. And these maneuvers are precise calculations in orbital mechanics, allowing the probe to spiral closer to the Sun without requiring massive amounts of onboard fuel. Venus plays an indispensable role in these accelerations. By borrowing angular momentum from the planet, the probe gradually increases its speed and adjusts its orbit. This interaction between spacecraft and celestial body showcases the elegant balance of forces governing our solar system. Without Venus's gravitational influence, such speeds and close approaches to the Sun would be unattainable. As the probe approaches the Sun, its velocity increases sharply to the star's immense gravitational pull. At its fastest, Parker travels nearly 200 times the speed of a commercial jetliner. This allows it to briefly hover in the outer layers of the Sun's corona, where it collects invaluable data on solar wind, plasma waves, and the interactions of magnetic fields. Parker Solar Probe's incredible speed not only facilitates close encounters with the Sun, but also drives groundbreaking discoveries in physics and astronomy. Observing solar phenomena at unprecedented scales and resolutions, the probe has shed light on the chaotic behavior of magnetic fields and the dynamics of charged particles. One of the key discoveries made possible by the probe's speed is its ability to observe switchbacks, zigzagging magnetic field structures that were previously elusive to slower solar missions. These phenomena may help explain how energy from the Sun's core is transferred to its outer atmosphere and accelerates the solar wind. The implications of these discoveries extend far beyond our solar system. By understanding how stars generate and distribute energy, researchers can apply this knowledge to other stellar environments. This could redefine our models of star formation, evolution, and the impact of stellar winds on exoplanetary systems. The Sun's corona is a realm of extremes, with temperatures reaching millions of degrees, hundreds of times hotter than the Sun's surface. While the corona's temperature can exceed a staggering 1.8 million degrees Fahrenheit, The surface, or photosphere, is only about 10,000 degrees Fahrenheit. This paradox, where the outer atmosphere is much hotter than its energy source, has baffled scientists for decades. Parker Solar Probe is transforming our understanding of this mystery, uncovering the hidden mechanics of the Sun's atmosphere. Recent data from the probe have brought scientists closer to solving this enigma. One of the most intriguing findings is tied to these magnetic switchbacks. The sudden reversals in the magnetic field observed in the solar wind indicate a dynamic and chaotic energy transfer system. Research suggests that these switchbacks may originate in the subalfinic corona and evolve as they move outward, influenced by reconnection events and plasma instabilities. Magnetic reconnection is a fundamental process occurring when magnetic field lines with opposite directions come into contact. Rather than passing through each other, the lines break and reconnect, releasing immense energy. This phenomenon not only plays a central role in the dynamics of the solar corona, but is also responsible for some of the most explosive events in the solar system, including solar flares and coronal mass ejections. The Parker Solar Probe's proximity to the Sun allows it to observe these reconnections as they occur, capturing their structure and energy signatures. Reconnection events often accelerate charged particles to near relativistic speeds, contributing to the intense heating of the corona and the formation of the solar wind. By analyzing these events, the probe provides insights into how magnetic energy is transformed into kinetic and thermal energy in plasma environments. Reconnection events are also linked to the formation of magnetic switchbacks, sudden changes in the solar wind's magnetic field direction. When the reconnection occurs in the subalfinic corona, this energy distorts magnetic waves, leading to the appearance of switchbacks. Moving outward, these distortions interact with plasma instabilities, amplifying their effects and contributing to the turbulent nature of the solar wind. Plasma instabilities add another layer of complexity to the Sun's behavior. These instabilities occur when changes in magnetic or kinetic energy disrupt the equilibrium of charged particles in the corona. For instance, during reconnection, plasma flows can become highly uneven, creating turbulence that propagates through the solar wind. The Parker Solar Probe has recorded evidence of these instabilities, including Alfvén waves, magnetic oscillations that travel through plasma like ripples on a pond. By studying these instabilities, the probe helps scientists understand how energy is transferred across the Sun's atmosphere on various scales. Of course, the solar wind itself, a stream of charged particles escaping the Sun's gravity, is also a primary focus of the probe. The spacecraft has detected bursts of energy driving this wind, offering insights into the processes that accelerate particles to high speeds. These observations are crucial for understanding how solar material travels vast distances, influencing planetary environments and interstellar space. Another breakthrough is the probe's contribution to modeling solar cycles. By mapping the Sun's magnetic field and its evolution, scientists gain deeper insights into the 11-year solar activity cycle. These models are vital for predicting periods of heightened solar storms, enabling better protection of our technology and infrastructure from potential disruptions. Particular attention should be paid to the fact that to achieve unprecedented proximity to our star, the Parker Solar Probe relies on the precision of gravitational assists, maneuvers, where the spacecraft uses Venus's gravitational pull to alter its trajectory. These flybys have been carefully calculated to reduce the probe's orbital energy, allowing it to spiral closer to the Sun. Each flyby of Venus modifies the probe's orbit, narrowing its trajectory around the Sun. During these encounters, the spacecraft approaches the planet's surface to within several hundred miles, utilizing Venus's gravity to fine-tune its approach. As a result of the most recent flyby in November 2024, the probe will come within 233 miles of Venus's surface, enabling it to achieve a record-breaking proximity to the Sun. The Venus flybys have yielded unexpected scientific results. Although Parker's mission is primarily focused on studying the Sun, its wide-range imager, WHISPER, has captured images of Venus's surface in visible and near-infrared light. These images reveal surface features such as Aphrodite Terra, Tellus Regio, and Io Planitia, faintly glowing through the planet's dense atmosphere. These observations not only corroborate earlier radar maps but also add new layers of detail. WHISPER's ability to detect brightness variations hint at chemical differences in surface materials, or even evidence of relatively recent volcanic activity. For instance, regions appearing brighter in WHISPER images may represent younger lava flows, offering clues about the planet's geological activity. In addition to surface imaging, Parker has captured the planet's atmospheric air glow, a luminous halo caused by oxygen atoms emitting light. These observations provide deeper insights into Venus's atmospheric composition and dynamic behavior, particularly its interaction with solar activity. One of the most intriguing discoveries during these flybys is the plasma tail trailing behind Venus. This structure, stretching thousands of kilometers, may explain how Venus has lost water over billions of years. Data collected by the probe's instruments indicate that the tail forms due to interactions with the solar wind, shedding light on the processes that transformed Venus from a potentially habitable planet into a scorched world. The Venus flybys not only refine the probe's trajectory, but also provide a wealth of data that deepens our understanding of Earth's enigmatic twin. 8 days after its record-breaking close approach to the Sun on December 24, 2024, the solar probe confirmed that its systems and scientific instruments were at full capacity and functioning normally, including the collection of scientific data during its journey around our star. Breaking its previous record, the spacecraft passed within just 3.8 million miles of the Sun's surface. Late Thursday evening, December 26th, the Mission Operations Center at Johns Hopkins Applied Physics Laboratory in Laurel, Maryland, received a beacon signal confirming the spacecraft had safely completed this leg of its journey. Telemetry data, which APL began receiving on January 1, 2025, provided more detailed information about the spacecraft's operational status. For example, it showed that Parker executed demands pre-programmed into its onboard computers before the flyby, and that its scientific instruments were fully operational during the event. The transmission of scientific data will begin later this month when the spacecraft and its most powerful onboard antenna are better aligned with Earth and capable of transmitting data at higher speeds. The next two close approaches to the Sun at roughly the same distance and speed will occur on March 22nd and June 19th. The Parker Solar Probe's mission to touch the Sun has been monumental, presenting numerous challenges that have tested the limits of engineering and scientific innovation. As the probe nears the Sun, it has faced not only extreme heat and radiation. In addition to enduring temperatures exceeding 2,500 degrees Fahrenheit, it must also withstand high-speed collisions with dust, traveling at an unprecedented speed of up to 430,000 miles per hour. The probe constantly faces the threat of impacts with cosmic dust. These high-speed collisions can create plasma clouds, potentially disrupting instrument functionality and overall spacecraft operations. Although the probe lacks a dedicated dust detector, it has still managed to gather valuable data on dust distribution near the Sun by analyzing these collisions. Overall, the data collected by the Parker Solar Probe has far-reaching implications for future missions and scientific research. Insights into phenomena such as solar wind, coronal heating, and magnetic fields enhance our understanding of stellar behavior. This knowledge is critical for developing predictive models of solar activity, which can profoundly impact space weather, satellite communications, power systems, and astronaut safety. Moreover, the engineering solutions developed for the Parker probe serve as a blueprint for designing future spacecraft intended to explore similarly extreme conditions. Among other things, the probe carries a memory card inscribed with the name Eugene Parker and a list of over 1 million names submitted by the public, symbolically allowing people to join this journey to the sun. The card also includes photographs of Dr. Parker and a copy of his 1958 scientific paper which first proposed the existence of the solar wind. Notably, the Parker Solar Probe is the first NASA mission named after a living person in recognition of his significant contributions of heliophysics. Overcoming immense challenges and embodying the aspirations of more than 1 million people, the Parker Probe is undoubtedly paving the way for future exploration, deepening our understanding of the sun and its influence on our home and on our solar system as a whole. Imagine a particle so elusive that trillions pass through you every second but leave no trace. A particle born in the fiery hearts of stars, in the cataclysmic collapse of supernovae, or perhaps in the first moments of the universe itself. These are neutrinos, tiny messengers from space, carrying secrets that could rewrite the laws of physics. But why are they so hard to detect? And what secrets can they reveal if we finally learn to listen to their whispers? Diving into the realm of these ghostly particles, we go where the known meets the unknown, and where the smallest particles hold the key to the biggest questions. The neutrino story begins in the early 1930s, when the study of particle physics was undergoing a revolutionary transformation. It was a time when the universe was revealing its secrets to those who dared to explore its mysteries. Wolfgang Pauli, an Austrian theoretical physicist, faced a problem. In beta decay, a type of radioactive decay observed in atomic nuclei, energy seemed to disappear. This disappearance contradicted the principle of conservation of energy, one of the most fundamental laws of physics. Pauli proposed a radical idea. What if the missing energy was carried away by an undetectable particle? He tentatively named this particle neutron, although Enrico Fermi soon renamed it neutrino to avoid confusion with the already discovered neutron. Fermi, an Italian physicist, was in turn instrumental in developing a theory describing this elusive particle and cementing its place in the scientific lexicon. Let's travel back to the Cold War era, a time when science and politics were closely intertwined. Neutrinos, once a mere theoretical curiosity, became the center of secret research projects driven by geopolitical tensions. The rivalry between the United States and the Soviet Union was not just about military might. It extended to the realm of science, where both sides sought breakthroughs that could give them an advantage. One such story is that of Bruno Pontecorvo, an Italian physicist who fled to the Soviet Union amid growing political tensions in the West. Pontecorvo had been heavily involved in neutrino research, and his defection caused a stir in both intelligence services and scientific circles. His departure led many to wonder if crucial information had been compromised, illustrating the distrust and anxiety of the Cold War era, and the extent to which neutrino research had become the subject of international intrigue. This period was marked by secret experiments, some conducted deep underground in abandoned mines or remote locations, where scientists were trying to catch these ghostly particles. Neutrinos, while among the most common particles in the universe, are also among the most elusive. These tiny particles are incredibly light and have such a small mass that for a long time it was thought to be zero. Unlike other fundamental particles, neutrinos interact only through the weak nuclear force and gravity, making them extremely difficult to detect. They pass through ordinary matter as if it were not there. Trillions are passing through you right now, completely undetected. 3 types or flavors of neutrinos are known: electron, muon, and tau neutrinos. Each is associated with a corresponding charged particle. electron, muon, and tau. But what makes neutrinos truly fascinating is their ability to oscillate between these flavors. This phenomenon, known as neutrino oscillation, was a revolutionary discovery because it suggested that neutrinos have mass, a fact not accounted for in the original standard model of particle physics. Neutrino oscillation occurs because neutrinos exist in a quantum superposition of different mass states. When a neutrino travels through space, it can move between these mass states, resulting in a change in flavor. This discovery not only won the 2015 Nobel Prize in Physics, but also pointed out gaps in the standard model, changing our understanding of fundamental physics. Neutrinos are also key players in some of the most dramatic processes in the universe. At the heart of a star, nuclear reactions generate huge numbers of neutrinos, which then leave the star almost instantaneously, taking energy with them. Neutrinos are the first particles to fly out of a dying star, signaling the start of a supernova. These particles provide crucial information about the processes taking place in the core, long before the light can escape. When a massive star reaches the end of its life cycle, its core collapses, leading to a supernova explosion. During this cataclysmic explosion, an enormous number of neutrinos are produced, orders of magnitude greater than the energy emitted by light. These neutrinos leave the supernova almost instantly, spreading through space, and some of them eventually reach Earth, giving a glimpse into these distant, violent events. There's also speculation that neutrinos may be linked to one of astrophysics' biggest mysteries, dark matter. Some theories suggest that a type of neutrino, perhaps a sterile neutrino, that does not interact with any known fundamental force other than gravity, may make up dark matter, the invisible mass that makes up most of the universe's matter. Although this remains an area of intense research, the possibility that neutrinos could unlock the secrets of dark matter emphasizes their importance to our quest to understand the cosmos. So the hunt for high-energy neutrinos has taken scientists to some of the most extreme places on Earth. Deep in the ice of Antarctica stands the IceCube Neutrino Observatory, scanning the cosmos for these elusive particles. Neutrinos, especially at extremely high energies, are the messengers of some of the most violent events in the universe, events that are still cloaked in mystery. Recent research has begun to peel back the layers of this mystery, pointing to active galactic nuclei, or AGNs, as significant sources of these high-energy neutrinos. AGNs are the luminous centers of galaxies powered by supermassive black holes. When matter falls into these black holes, it releases huge amounts of energy, often forming jets of high-speed particles. However, recent discoveries show that these jets may not be the only source of neutrinos. In 2022, the galaxy NGC 1068 was identified as a likely source of high-energy neutrinos, a discovery that surprised many in the scientific community. The neutrinos were traced to the galaxy's core, where a supermassive black hole is hidden behind thick layers of dust and gas. This discovery disproved the popular belief that such neutrinos can only be emitted by galaxies with bright jets, such as blazars. The surprises didn't end with NGC 1068. Further studies revealed two more galaxies, NGC 4151 and NGC 3079, as potential sources of high-energy neutrinos. The findings strongly suggest that the environment around supermassive black holes and these active galaxies is a powerful neutrino factory. These findings have led to a paradigm shift in our understanding of where high-energy neutrinos come from. As the search for these cosmic messengers intensifies, so does the competition between the world's most advanced neutrino detectors. IceCube has already made remarkable discoveries, but other projects are on the horizon that aim to push the boundaries of our knowledge even further. In Japan, the Hyper Kamiokande is poised to become a leader in neutrino detection. This huge underground detector, located in a cave specially dug for the purpose, will be filled with 260,000 tons of ultraviolet water. The goal is to capture fleeting flashes of Cherenkov radiation produced when neutrinos interact with water molecules, a technique honed over decades of Japanese research. Meanwhile, in the US, the Deep Underground Neutrino Experiment, also known as DUNE, is being built in an old gold mine in South Dakota. Unlike Hyper-K, which uses water, DUNE will utilize a state-of-the-art time projection camera in liquid argon. This technology promises to capture neutrino interactions with unprecedented precision, allowing scientists to map neutrino properties in great detail. Although both the Hyper-Kamiokande and DUNE share the common goal of solving the mysteries of neutrinos, their approaches differ significantly. Hyper-K is based on proven technologies and aims at mass data collection. On the other hand, relies on innovative technologies that can reveal new aspects of neutrino behavior. The stakes are high. Both projects seek to answer fundamental questions about the universe, such as the origin of matter itself. One of the key areas of research will be a phenomenon known as charge parity violation, which may explain why the universe is composed mainly of matter rather than antimatter. Charge parity violation, CP, could be the key to solving this cosmic mystery, and Hyper-K and DUNE are designed to find it. By comparing the oscillations of neutrinos and their antimatter, antineutrinos, as they pass through space, these detectors can show whether there's a fundamental difference in the behavior of matter and antimatter. But the race to find CP violation is also a race against time. Hyper-Kamiokande is expected to begin collecting data as early as 2027, which could give it an edge over DUNE, which is not expected to be fully operational until the early 2030s. The competition between these two experiments could determine the future of neutrino physics for decades to come. The Standard Model of particle physics has long been considered one of the most successful theories in science, providing a framework for describing the fundamental particles and forces that make up the universe. However, even this robust model has its limitations, and nowhere is this more apparent than in the study of neutrinos. These elusive particles, which have almost no interaction with other matter, have properties that push the boundaries of our understanding. One of the most serious challenges to the Standard Model comes from the discovery that neutrinos have mass. According to the original scheme, neutrinos were thought to be massless, but the observation of neutrino oscillation, when neutrinos change from one type to another, proved otherwise. This discovery alone was enough to shake the foundations of the Standard Model. But that was not all. The consequences of the appearance of neutrino mass go beyond a simple revision of the model. They suggest the possible existence of a new type of neutrino, the sterile neutrino. Now, we've already mentioned this in passing, but here's the gist of it. Unlike the three known types of neutrinos, electron, muon, and tau, which interact through the weak nuclear force, sterile neutrinos interact only through gravity. This makes them even more difficult to detect, but their existence may well explain several mysteries in physics. If sterile neutrinos are shown to exist, they'd not only call into question the completeness of the Standard Model, but would open the door to entirely new physics. This would require extending the model to include these new particles, potentially leading to a more unified theory of the fundamental forces. Neutrinos may also provide clues to another profound mystery, the scarcity of antimatter in the universe. According to current theories, the Big Bang should have produced equal amounts of matter and antimatter. But today we observe a universe in which matter predominates and antimatter is rare. This imbalance is one of the great mysteries of cosmology. One theory suggests that neutrinos and their antimatter, antineutrinos, may behave differently. If neutrinos do break this symmetry, this could later explain why there is more matter than antimatter left after the Big Bang. The T2K experiment in Japan has provided tantalizing evidence for CP violation in neutrinos. In this experiment, beams of neutrinos and antineutrinos are sent on a 185-mile, 300-kilometer journey across Japan to the Super Kamiokande detector. For nearly a decade, researchers have noticed that neutrinos oscillate into different types more often than antineutrinos, suggesting that they may indeed behave differently. This potential CP violation in neutrinos could be the missing piece to explain why the universe is made up mostly of matter. However, the current results, while promising, are not yet conclusive. The level of statistical significance required to recognize a discovery in particle physics is 5 sigma. The T2K results have only reached about 3 sigma, and this means that although the evidence is strong, it's not absolute. To truly confirm the CP violation in neutrinos and unlock the secrets of antimatter rarity, scientists are turning to the next generation of neutrino detectors. Hyper-K in Japan and DUNE in the US are poised to take this research to the next level. These massive detectors will collect many times more data with greater accuracy, potentially reaching the 5 sigma threshold. If these experiments confirm CP violation in neutrinos, it could revolutionize our understanding of the origin of the universe and answer one of the most persistent questions in science: why there is something rather than nothing. The study of neutrinos, once considered an obscure branch of physics, may ultimately hold the key to understanding the very fabric of our reality. To answer some of physics' deepest questions, scientists are developing the next generation of detectors, each more advanced than the last. One of the most ambitious projects in this field is the Karlsruhe Tritium Neutrino Experiment, or CATRIN, in Germany. The CATRIN project has one goal: to measure the mass of neutrinos. The experiment aims to observe the beta decay of tritium, a radioactive isotope of hydrogen, to determine the tiny neutrino mass. By analyzing the energy of the electrons emitted in this decay, CATRIN aims to set an upper limit on the neutrino mass, pushing the boundaries of discernibility. CATRIN has already made significant progress, setting an upper limit on the neutrino mass of 0.8 electron volts, with sensitivity down to 0.2 electron volts. However, this may not be sufficient to determine the true neutrino mass, which may be even smaller. This realization has sparked a global effort to develop alternative methods and experiments that could surpass the capabilities of CATRIN. Among these alternative approaches is the use of holmium-163 in electron capture experiments. Unlike tritium, holmium-163 decays via electron capture when an electron is absorbed by the nucleus, resulting in the emission of a neutrino and a photon. This releases a minuscule amount of heat that can be detected by extremely sensitive equipment. Experiments with holmium-163 have already demonstrated highly accurate energy measurements, and physicists aim to increase their sensitivity by an order of magnitude. Another promising direction is the Project 8 experiment, which uses a magnetic bottle to capture electrons from beta decay in gaseous tritium. By analyzing the radio waves emitted by these captured electrons, researchers can obtain precise measurements of their energies. Project 8 aims to achieve a sensitivity of up to 0.04 eV, which could surpass the limit set by cosmological studies and provide crucial data on the true mass of neutrinos. The quest to understand neutrinos is not confined to one country or continent. It's truly a global endeavor. The challenges posed by these elusive particles have brought together scientists from around the world, fostering collaboration across borders. As we await the first signals from Japan's Hyper-K, which is already taking shape in a newly dug cave, and await news from DUNE, nestled deep in an old South Dakota gold mine, the next chapter in our understanding of the universe is just beginning. Stay tuned as we journey through the frontiers of science, making one discovery at a time. Supernovae are not just amazing events in the universe. They're vital cosmic phenomena that shape and create galaxies. These powerful explosions occur at the end of a massive star's life cycle, ejecting elements into space from which new stars, planets, and even life itself are formed. In essence, supernovae serve as both destroyers and creators of galaxies. In the study of supernovae, imagery plays a crucial role in understanding these powerful explosions. Over the years, advances in imaging technology have allowed astronomers to capture spectacular views of supernovae at different stages, revealing intricate details of their structure and the elements they eject into space. The story of Betelgeuse, a red supergiant star, is a prime example of how images help us understand the behavior of supernovae. Betelgeuse has recently attracted a lot of attention due to its sudden fades and increases in brightness. This variability has led to speculation of its imminent explosion, sparking widespread interest. The appearance of a dust cloud around the star, observed in telescopes and captured on images, was initially taken as a precursor to a supernova. However, later it began to be considered as a natural phenomena in the life cycle of red supergiants. So why did scientists initially hypothesize the possibility that this star would be the next observed supernova? This red supergiant occupies a prominent place in the constellation of Orion, perched on its shoulder, and is visible to the observer even to the naked eye. Let's take a look at the life cycle of Betelgeuse, an intriguing journey that will show the evolution of the star from its birth to its current state as a massive, pulsating giant nearing the end of its life. Betelgeuse began its existence as a massive star burning hydrogen in its core, like many others. However, because of its large mass, it evolved rapidly, entering successive phases of nuclear fusion. The significant mass of the star distinguished its evolutionary path from the evolution of smaller stars, such as our Sun. While the Sun is currently a stable main-sequence star slowly converting hydrogen into helium, Betelgeuse, due to its much larger mass, more quickly depleted its hydrogen reserves and evolved into a red supergiant. The key difference between Betelgeuse and our Sun is their masses. Betelgeuse, which has about 15 to 20 times the mass of the Sun, experiences higher pressure and temperature in its core, which accelerates nuclear fusion. Intense fusion causes Betelgeuse to burn its fuel rapidly, resulting in an unstable structure and significant brightness fluctuations. In contrast, the Sun's lower mass allows it to remain stable for billions of years, with a much longer and more stable hydrogen burning phase. As Betelgeuse aged, it entered successive phases of nuclear fusion, gradually burning off elements heavier than hydrogen. Internal pressure caused the star to begin to swell, transforming it from a main-sequence star into a red supergiant. This stage is characterized by Betelgeuse's enormous size and variability in brightness. The star expands and contracts as it undergoes complex nuclear processes. Recent observations have suggested that Betelgeuse may be on the verge of a supernova. The star's dimming in 2019, followed by an unexpected increase in brightness, has led scientists to speculate that it may be approaching the final stage of its life. These changes in brightness are thought to be related to internal processes, possibly signaling the beginning of core collapse. The star's pulsations, with cycles of 185, 230, 420, and 2200 days, were analyzed to understand its internal dynamics. The longest cycle of 2200 days is particularly intriguing because it may represent Betelgeuse's fundamental pulsation mode, indicating its advanced stage of evolution. These observations, along with recent telescopic findings, suggest that Betelgeuse may be entering a phase of carbon combustion that precedes a supernova explosion. But what are the complex nuclear processes that dictate when a star's life must come to an end? At the center of a massive star like Betelgeuse, nuclear fusion turns hydrogen into helium, releasing enormous energy. As the star ages, heavier and heavier elements fuse to form bulb-like layers. Eventually, the core is filled with iron, which cannot release energy during the fusion process, leading to gravitational collapse. As the core collapses, a runaway reaction is triggered. In this process, the iron core collapses under enormous gravitational forces, reaching temperatures of billions of degrees. This leads to the rebound effect, where the core inflates and then explodes, creating a shockwave that rips the star apart. A supernova explosion releases an enormous amount of energy, briefly eclipsing an entire galaxy. The mechanics of this process involve a complex interplay between nuclear collapse, gravitational forces, and intense heating. The shockwave generated by the collapse of the core propagates outward, ejecting the outer layers of the star into space. Ancient astronomers have recorded these bright phenomena for thousands of years, sometimes describing them as guest stars or new stars. The earliest recorded supernova observation dates back to 185 AD when Chinese astronomers observed guest stars, as they called them, that were visible for 8 months. Although rare, astronomers continue to study them to this day, especially when they lead to unusual phenomena such as gamma-ray bursts. Gamma-ray bursts, or GRBs, are intense bursts of gamma rays, usually associated with the collapse of massive stars or the merger of neutron stars. These bursts are some of the most energetic events in the universe, capable of releasing more energy in just a few seconds than the Sun will emit in its entire 10 billion year lifetime. The discovery of the Boat GRB, also referred to as the brightest of all time, in October 2022, was a milestone in GRB observations, stunning astronomers with its unprecedented brightness and startling impact on Earth. The Boat GRB, officially designated GRB 221009A, was detected on October 9, 2022, and originated from a galaxy about 2.4 billion light-years away from Earth. The event was unusual not only in its brightness, but also in its duration. It lasted about 7 minutes, much longer than a typical gamma-ray burst. The burst was so powerful that it affected the Earth's ionosphere, temporarily disrupting radio communications and altering the ionization of the atmosphere. The relationship between supernovae and gamma-ray bursts is complex and fascinating. In some cases, the collapse of the core of a massive star can trigger a GRB, especially if the star is rapidly rotating and has a strong magnetic field. Such long GRBs often last more than 2 seconds and are often followed by a supernova explosion. Boat was notable not only for its brightness but also for providing insight into the formation of heavy elements. In April of this year, scientists studied this burst in detail, initially hoping that it might provide clues about the origin of elements heavier than iron, which are usually formed in supernova explosions or neutron star mergers. However, further analysis showed that GRBs do not produce these elements, leaving scientists even more puzzled and emphasizing the mysterious nature of cosmic phenomena. To find out exactly what caused the flare, scientists used a variety of observational tools, including the James Webb Space Telescope. The exceptional brightness of the flare initially obscured its surroundings, making it difficult to observe the accompanying supernova or other objects in the host galaxy. It took several months before the brightness diminished enough to make detailed observations possible. As a result, a relatively undetectable supernova remnant was detected, which was surprising given the power of a gamma-ray burst. The Boat GRB also provided insight into the characteristics of gamma-ray bursts. The exceptional brightness and long duration of this event indicated that the GRB was very focused, with narrow jets pointing directly toward Earth. This narrow directivity likely contributed to the observed intense brightness, as gamma-ray bursts tend to be directional phenomena. The narrow burst jets were probably the result of a rapidly rotating star with a strong magnetic field that produced a powerful and focused flare. While both GRB has provided insight into gamma-ray bursts and supernovae, scientists continue to find answers to the mysteries of Betelgeuse. Recent research suggests that Betelgeuse's cycles of dimness and brightness are part of its natural behavior as a variable star. It turns out that, unlike our Sun, Betelgeuse is an extremely explosive and low-density plasma cloud that changes shape frequently. Created by scientists, simulation illustrates the behavior of Betelgeuse in time. Periods of brightness and dimness occur about every 400 days, and the longer cycle is about 2,000 days. Recent studies have tried to explain the Great Dimming phenomena that occurred in 2020, and observations from various telescopes over the past 15 years have provided much insight. Observations at various frequencies, including microwaves and infrared, have allowed scientists to penetrate the layers of Betelgeuse and detect silicon monoxide, indicating the presence of a large dust cloud. This discovery disproved initial speculation that Betelgeuse was about to explode. Instead, it appears that internal activity within the star has caused the material to separate, forming a large gas cloud. The formation of a cold region beneath this cloud caused particles to condense, creating a dark cloud that obscured Betelgeuse from view from Earth. Further study of Betelgeuse's behavior revealed that the star experienced two shockwaves, one in 2018 and another 1 year later. These waves disrupted the surface, creating hot and cold spots, which was confirmed by Hubble Space Telescope ultraviolet imaging observations. The shockwaves and their aftermath disproved the initial assumption that Betelgeuse was close to a supernova, and instead showed that this behavior of the star is part of its natural life cycle. Betelgeuse's behavior is also characterized by its high rotation rate. Unlike typical red supergiants, which rotate slowly, Betelgeuse rotates at about 3 miles per second, which initially led researchers to think that it might have been a binary star that collided. However, recent research suggests that this rotational speed may be influenced by fast-moving convective cells inside the star, contradicting initial assumptions about its rotational behavior. Despite the unusual behavior, this research suggests that Betelgeuse is unlikely to become a supernova in our lifetime. The current state of the star is more like a variable red supergiant nearing the end of its life, but by no means approaching a supernova explosion. So finally we come to the very question that concerns all of us. How would such an explosion affect our home planet? The potential impact of a nearby supernova on Earth is a subject of speculation and concern. While a supernova is not expected to pose an immediate threat to our home, the explosion of a star within a few light years could affect Earth's atmosphere and potentially impact life. For example, the flare of the very same boat GRB was so intense that it significantly affected the Earth's ionosphere, altering atmospheric conditions and disrupting radio communications. The flash released a tremendous amount of energy that interacted with the Earth's atmosphere, causing a sudden increase in ionization. This increased ionization affected the ozone layer and triggered chemical reactions that scientists are still trying to understand. The GRB also disrupted radio signals, especially those used for communication and navigation. The energy released in the explosion was so great that it even blinded several satellites, demonstrating the enormous power of these cosmic phenomena. However, the burst itself was observed from a galaxy a whopping 2.4 billion light-years away. This event only emphasizes the need for further study of gamma-ray bursts to understand their impact on us, our planet, and the universe as a whole. In addition, supernova studies also contribute to our understanding of dark matter dark energy, and the overall structure of the universe. Type 1a supernovae, which occur in binary star systems, are crucial for measuring cosmic distances and studying the expansion of the universe. These standard candles have helped astronomers detect the accelerating expansion of the universe, which in turn has provided the background for understanding dark energy. Supernovae are a key focus of future astronomy. Their explosive nature and transformative impact continues to fascinate scientists and inspire discovery. Well, while some people are frozen in anticipation of the Betelgeuse explosion on live internet feeds, we look forward to discoveries from missions such as the Vera Rubin Observatory and the European Space Agency's Euclid telescope, which will contribute to advancing our understanding of supernovae. As we look deeper into space, these stellar explosions will undoubtedly shape our understanding of the universe and our place in it. Amidst the peace and tranquility of the celestial bodies of the solar system, there is one object that greatly disturbs the peace of the rest: the Moon, Io. Unlike any other orbiting the mighty Jupiter, shrouded in mystery, Io is a world of fire and fury, a stark contrast to the icy moons and calm planets that share its cosmic neighborhood. This mysterious moon, the most volcanic body in our solar system, is a testament to the dynamic forces at work in the cosmos. Its surface, riddled with hundreds of active volcanoes, tells the story of the relentlessly complex gravitational pull of Jupiter and other moons. Meet Juno, NASA's intrepid explorer, on a journey to this fiery world. Its mission is to unravel the mysteries of Io, capture its fiery essence, and uncover the secrets that have long lurked beneath its tumultuous surface. As Juno makes its closest approach in 2 decades, we stand on the threshold of new discoveries and are ready to unravel the mysteries of this volcanic moon. What will Juno tell us about Io's turbulent volcanoes? How does the turbulent nature of this moon affect giant Jupiter and its other moons? And what can Io tell us about the forces that shape our solar system? Let's find out. Discovering new space vistas, Juno, a spacecraft made not only of metal and circuitry but also of ambition and curiosity, is embarking on a journey that hasn't been taken in more than 2 decades. For the first time in 20 years, a spacecraft dares to come so close to Io that we can come face to face with a world of extreme volcanic activity. Juno's close is not just a routine flyby, but a bold dive into the unknown. The spacecraft, equipped with state-of-the-art instruments, is designed to withstand the harsh radiation environment of Jupiter and its moons. As it approaches the rough surface of Io at a distance of 930 miles, Juno's sensors come to life, taking high-resolution images and collecting valuable data. In late 2023, the probe made its closest flyby of Io, taking some incredible images in the process. In them, Jupiter's moon appears to glisten with sulfuric hues, and its surface is speckled with spots created by the ongoing volcanic activity that rages on it. By combining data from this flyby with our previous observations, the Juno science team is studying how Io's volcanoes vary, says astronomer Scott Bolton of the Southwest Research Institute. We are looking for how often they erupt, how bright and how hot they are, how the shape of the lava flow changes, and how Io's activity is connected to the flow of charged particles in Jupiter's magnetosphere. The heart of this mission lies in the technological prowess that Juno possesses. The spacecraft's JunoCam continues to take spectacular images despite the challenges of Jupiter's intense radiation. The Stellar Reference Unit's Stellar Navigation Camera is also a scientific instrument, providing the highest resolution images of Io's surface to date. On Earth, scientists are studying the data coming from Juno. Each byte of data is a piece of the puzzle, revealing new information about the volcanic nature of Io. Analyzing this is a window into our solar system's past, present, and future. So, late last year, NASA's Juno probe took the highest resolution images of this moon to date. Among these images, one that stands out is one taken on December 30th, which vividly depicts the volcanic nature of Io. This image, enhanced to emphasize details, shows a volcanic plume erupting from Io's surface, with plumes reaching more than 60 miles, given that the moon's diameter is about 2,200 miles. As Juno continues its journey around Jupiter, each orbit brings new opportunities, new challenges, and new discoveries. Among the planet's other 95 moons, Io stands out not only for its proximity to Jupiter, but also for the dramatic geologic activity that this proximity provokes. The volcanic nature of the moon is a direct consequence of Jupiter's enormous gravitational forces. Io is not a huge moon. It's only slightly larger than the one orbiting our planet. However, as the largest planet in our solar system, Jupiter has tremendous gravity. This enormous force stretches and squeezes Io, creating what is known as tidal heating. The satellite's orbit itself is not a perfect circle, resembling more of an ellipse, so the moon experiences varying degrees of gravitational pull from Jupiter. As it approaches Jupiter, the planet's gravity stretches Io, and as it moves away, it compresses it. This constant stretching creates tremendous internal heat within Io, leading to its intense volcanic activity. This JunoCam image captures a plume of material ejected from the unseen volcanic Prometheus. Indicated by the red arrow, the plume is just visible in the darkness below the terminator, the line dividing day and night. The image was taken by spacecraft on October 15, 2023. Tidal heating is so intense that it turns Io's interior into a bubbling cauldron of molten rock. This heat leads to the volcanic activity that defines Io's landscape. Hundreds of volcanoes dot its surface, some of them spewing lava fountains up to hundreds of kilometers high. There are about 400 active volcanoes on Io, about 150 of which are erupting at any given time. But Jupiter is not the only player in this gravitational confrontation. The other Galilean moons, Europa, Ganymede, and Callisto, also exert their influence on Io. Their gravitational attraction helps to maintain Io's elliptical orbit, thus playing a crucial role in the tidal heating process. This complex gravitational interaction is a perfect example of how celestial mechanics determine the fate of a moon. The tidal forces of Jupiter and its moons don't just heat Io, they create a world in which geologic activity is the norm, not the exception. Io, a moon shrouded in fire and brimstone, plays a key role in the grand theater of Jupiter's system. Its incessant volcanic activity not only shapes the landscape, but also significantly affects the very nature of Jupiter's magnetosphere. As we mentioned earlier, the volcanoes on this satellite are the most active in the solar system. In doing so, they spew huge amounts of sulfur dioxide, or SO2, into space. This outgassing, a direct result of intense internal heating, contributes to an atmosphere rich in sulfur compounds. But Io's influence extends far beyond its own atmosphere. As Io rotates within Jupiter's massive magnetosphere, sulfur dioxide and other volcanic gases ionize, becoming charged particles. These particles become trapped in Jupiter's magnetic field, forming a plasma torus along Io's orbit. This torus, a glowing ring of ionized particles, is a direct manifestation of the moon's volcanic power. The plasma torus is not a static feature. It changes in response to Io's volcanic activity. The ejection of material from volcanoes feeds the torus, affecting its density and composition. This complex interaction between Io's volcanism and the plasma torus illustrates the interconnectedness of Jupiter's system. It's also thought to be responsible for powerful, permanent auroras at the planet's poles. Volcanic emissions, once in the atmosphere, escape into space. Here they undergo rapid reneutralization, a process that ejects these particles at high velocity in a plane perpendicular to the local magnetic field. This phenomenon continues to the formation of extended sodium nebulae, adding another layer to the complex environment around Jupiter. Observational studies have been crucial in shedding light on these interactions. For many years, telescopes, like TRAPPIST, have followed the variability of Io's sodium cloud. These observations have shown that the physical properties of the sodium jets from Io are highly variable and, interestingly, do not always correlate directly with the global brightening of Jupiter's plasma torus or the extended sodium nebula. This study highlights the complexity of the surface-atmosphere-magnetosphere coupling in the Jupiter system. Current research aims to reveal the precise mechanisms by which Io's volcanoes supply material to the plasma torus, and how Io's sodium jet contributes to filling the plasma reservoirs of the magnetosphere. Thus, Io's relentless volcanic activity and its interaction with Jupiter's magnetic fields are not just isolated phenomena. They play a fundamental role in shaping the dynamics of Jupiter's magnetosphere, producing plasma structures and neutron clouds that are key to understanding the complexities of planetary magnetospheres. Ongoing research and observations allow us to separate the layers of these interactions, offering a deeper understanding of the workings of our solar system. As we look to the future of space exploration, the fiery moon Io appears as a beacon of mystery and potential. The next phase of Io exploration is poised to reveal secrets that have remained hidden beneath its stormy surface for centuries. Introducing the Jupiter Icy Moons Explorer mission, abbreviated as JUICE. JUICE aims to study Jupiter's icy moons, offering intriguing opportunities to further our understanding of Io. Although JUICE's primary focus is on Ganymede, Europa, and Callisto, its extensive suite of instruments can provide valuable insights into Io's dynamic environment. The interplanetary spacecraft was launched on April 14, 2023, from the Guiana Space Center in French Guiana by the European Space Agency. The spacecraft is expected to reach Jupiter in July 2031 after 4 gravity assists and an 8-year journey. As JUICE passes through the Jupiter system, its trajectory may provide opportunities to observe Io. These encounters may provide additional data on the satellite's volcanic activity and its effect on Jupiter's magnetosphere, complementing the conclusions drawn by missions directly targeting Io. Equipped with sophisticated instruments designed to study magnetic fields, plasma environment, and atmospheric composition, JUICE has the potential to indirectly expand our knowledge of Io. By studying Jupiter's magnetosphere and the interactions within it, JUICE can provide a broader context for the satellite's role in the entire Jupiter system. Another mission, Io Volcano Observer, or IVO, is a bold initiative that represents the next leap in our quest to understand this volcanic moon. IVO is a proposed mission designed to study Io's intense volcanic activity, its subsurface structures, and the complex processes that drive its geologic dynamism. IVO's mission is to enter orbit around Io and make multiple close flybys. Equipped with state-of-the-art instruments, IVO will map Io's volcanic heat flows, study lava composition, and probe the moon's internal structure. This mission aims to answer fundamental questions about the mechanisms of volcanism on Io and the role of tidal heating in its activity. One of the most interesting aspects of the IVO mission is exploring the bowels of the moon. What lies beneath its fiery facade? IVO seeks to shed light on this mystery by studying the moon's internal structure. Seismic measurements and magnetic field analysis may reveal the presence of subsurface magma chambers and provide insight into the moon's volcanic flow system. The potential for new discoveries about Io's volcanic mechanisms is enormous. IVO observations could revolutionize our understanding of volcanic processes, not only on Io, but throughout the solar system. By studying Io's unique volcanism, we'll be able to gain insight into the thermal evolution of planetary bodies and the role of tidal forces in shaping planetary geology. In the meantime, Juno continues to work, with many more observations planned. not only of Io, but also of the other Galilean moons, and, of course, Jupiter itself. The spacecraft will continue to operate until September 2025, or until it breaks down, whichever comes first. In the meantime, we'll look forward to more images taken by the next flyby. In the vast theater of our solar system, where planets like Jupiter and Saturn often attract attention with their majestic rings and violent storms, lies a distant world shrouded in mystery and intrigue. This is Uranus, an enigmatic ice giant that often goes unnoticed, but holds secrets that may unravel some of the most enduring mysteries of the cosmos. Far beyond the asteroid belt, nestled between the orbits of Saturn and Neptune, Uranus travels through the cold and dark corners of our solar system. It's a world that lives at a different rhythm, spinning on its side, an oddity that's long puzzled astronomers and spawned countless theories. Discovered in 1781 by William Herschel, Uranus was the first planet discovered through a telescope, extending the known boundaries of our solar system. For centuries, this distant world was just a speck of light in our telescopes, a ghostly blue ball, distant and aloof, keeping its secrets. But now, with the advent of the James Webb Space Telescope, a new chapter in the exploration of Uranus is opening. JWST, with its unprecedented vision, peels back the layers of this icy giant, revealing a world of amazing beauty and complexity. Let's travel together to this mysterious ice giant and learn about the latest discoveries made by the James Webb Space Telescope. In the quest to understand the universe, humankind has launched a Sentinel into space, a marvel of engineering and a testament to our insatiable curiosity. This Sentinel is the James Webb Space Telescope, the most advanced and powerful space telescope ever built, the successor to the legendary Hubble Space Telescope. Equipped with a set of advanced instruments and a mirror more than 6.5 meters in diameter, JWST is designed to observe the universe in light invisible to the human eye, the infrared spectrum. This allows the telescope to peer through clouds of cosmic dust, discover distant galaxies, and study the atmospheres of exoplanets. The telescope's journey into space was a feat in itself. Launched on an Ariane 5 rocket, JWST traveled to a point in space known as the Second Lagrange Point, or L2, 1,000,000 miles from Earth. Here, in this stable orbit, JWST can observe the universe with minimal interference from Earth and the Sun. JWST's capabilities are not limited to observing the early universe or distant galaxies. It plays a key role in unlocking the mysteries of our solar system. Its powerful instruments, such as the Near-Infrared Camera, NIRCam, and the Mid-Infrared Instrument, MIRI, reveal new details about planets, moons, and other celestial bodies closer to home. Take Uranus, for example. In the past, our view of this distant planet was limited to faint images from telescopes such as Hubble. But now, thanks to JWST's enhanced infrared capabilities, we can see Uranus in a new light. The telescope's sensitive instruments allow us to observe the planet's atmosphere, weather patterns, and even its mysterious rings with unprecedented clarity. By analyzing the light of Uranus, JWST can decipher the chemical composition of its atmosphere, revealing the presence of gases such as methane and hydrogen. This not only helps us understand the current state of Uranus, but also provides clues about its formation and evolution. The James Webb Space Telescope continues to exceed expectations, revealing more details about our universe every day. Its latest triumph is a series of images of Uranus taken very recently, surpassing even the stunning observations made in April 2023. In early 2023, JWST provided us with unprecedented views of Uranus, allowing us to look at the planet's atmospheric dynamics and ring system in a new light. The recent images, however, are a step further. Not only are they clear, they reveal aspects of Uranus that were previously hidden or obscured, even in April observations. Take the rings of Uranus, for example. The latest images show them with even greater clarity. We can now observe finer structures within the rings and even detect faint dust bands that were previously invisible, such as the Zeta ring, the incredibly thin ring closest to the planet. The strength of JWST lies not only in its one-off observations, but also in its ability to continuously track celestial objects. Continuous observations of Uranus have allowed us to observe changes in the planet's atmosphere, track the movement of its clouds, and observe the evolution of its storms over time. The changes in the polar regions are particularly striking. Bright white caps and dark bands near the poles, the origin of which is still unclear, have shown marked changes. This continuous observation provides invaluable data for understanding the seasonal changes and long-term climate patterns of Uranus. In the set of planets in our solar system, Uranus stands out with a peculiar feature, an extraordinary axial tilt. Unlike any other planet, Uranus rotates practically on its side, tilted at an angle of about 98 degrees. This unique orientation has long intrigued astronomers and sparked a quest to understand its origin and consequences. To understand the significance of this tilt, we must travel back in time to the early days of our solar system. Uranus probably formed with a much less severe tilt. The prevailing theory suggests that a catastrophic event, perhaps a collision with a planet-sized object, dramatically changed its orientation. This colossal impact would have thrown Uranus aside, changing the definition of its axis of rotation. Such a dramatic event in the planet's history probably not only changed its rotation, but also left an indelible mark on its entire system, including its satellites and rings. Today, this lateral rotation is a unique spectacle. Each pole of Uranus is alternately flooded with sunlight and plunged into darkness at intervals of 42 years. This extreme tilt results in extreme seasons, unlike those observed on other planets. The implications for planetary observations and research are enormous. Uranus's tilt allows us to observe its rings and satellites from different perspectives, offering insights into their composition and dynamics. For example, when Uranus's rings face the Earth, they become nearly invisible, exposing fainter dust bands and smaller satellites. Compare that to Earth, which is tilted only 23.5 degrees. Uranus's extreme tilt causes drastic changes in its weather patterns, which is a goldmine for scientists studying planetary climate. Tilt also affects the circulation of Uranus's atmosphere. Prolonged exposure to sunlight at the poles can result in complex weather systems, as seen in recent JWST images. These systems are very different from those on other planets and provide a unique laboratory for understanding atmospheric physics. Let's take a journey on one Uranian year. Each season on Uranus lasts about 21 Earth years, a consequence of its 84-year orbit around the Sun. This extended duration means that each hemisphere experiences long periods of daylight, followed by equally long nights. As a result, the planet undergoes dramatic changes in appearance and climate. Because one pole of Uranus basks in uninterrupted sunlight, summers are long, while the opposite pole plunges into a deep, dark winter. This stark contrast creates unique atmospheric conditions, causing complex weather patterns and climatic shifts. The impact of these seasonal changes on Uranus's atmosphere is profound. When the sun illuminates the planet's surface, it warms the atmosphere, creating colossal storms and dynamic cloud systems. These atmospheric phenomena are not static. They evolve and change with the seasons, painting an ever-changing portrait of the planet. Among the most striking features are the bright cloud tops that appear when the sun illuminates the planet's atmosphere. These clouds, composed of frozen methane and other gases, reflect sunlight, creating a dazzling spectacle. Conversely, dark storm patches that look like giant hurricanes roam the planet's surface. Moreover, the planet's seasonal phenomena affect not only the planet itself, but also its moons. One recent study of Uranus's moons, or rather a phenomenon that's particularly intriguing, is the development of temporary atmospheres on these moons, a spectacle caused by the unique conditions of the Uranus system. The key to understanding these temporary atmospheres lies in the extreme tilt of Uranus's axis and its effect on the satellite's orbits. As these satellites orbit the planet, they experience dramatic changes in solar exposure, alternating between long periods of intense sunlight and prolonged darkness. During the long summer exposed to sunlight, the icy surfaces of these satellites undergo a process known as sublimation. The ice, composed mainly of water, methane, and carbon dioxide, transforms directly from solid to a gas, bypassing the liquid phase. This sublimation creates thin, temporary atmospheres, or exospheres, that envelop the satellites. These exospheres are most pronounced when moons are warmest. Recent research by the James Webb Space Telescope shows that this phenomena is more dynamic and complex than previously thought. Exospheres are heterogeneous. They vary in composition and density, depending on the topography of the moons and the intensity of solar radiation. As the satellites enter their winter phase, the exospheres gradually dissipate. Gases recondense on the surface, returning to an icy state. This cycle of atmosphere creation and disappearance is a unique characteristic of Uranus's satellites, opening a window into the interaction between solar radiation and surface ice. The rings of Uranus, often overshadowed by the majestic rings of Saturn, hold their own tale of cosmic intrigue and dynamism. A recent comparative study of the rings of Uranus, Saturn, and Jupiter sheds new light on these lesser-known, but no less fascinating, celestial features. In contrast to the wide and bright rings of Saturn, the rings of Uranus are narrow, dim, and less extensive, extending to 4 planetary radii. This includes elusive rings, such as the Mu and Nu rings. The study delves into the gravitational influence of Uranus's main satellites on these rings, a key factor in their formation and evolution. The significant influence of Uranus's 5 major satellites, Miranda, Ariel, Umbriel, Titania, and Oberon, plays a central role in the history of the rings. These satellites, much more massive than their smaller counterparts, dominate the gravitational dynamics within the Uranus system. Their positions and masses relative to Uranus provide a better understanding of the formation of the satellites and the gravitational formation of the rings. The formation of Uranus's rings is attributed to a combination of processes, including collisions, satellite breakup, and gas release from the main satellites. These dynamical processes affect the material composition of the rings and are influenced by the ever-changing environment of the Uranus system. The stability of the rings is intrinsically linked to their dynamical interactions with the satellites of Uranus. The study examines how accretionary processes occur within the Roche limit and how the dynamics of shepherding moons play a crucial role in maintaining the rings. In addition, the rings provide a unique opportunity to understand the internal structure of Uranus through seismological studies. Modeling results show how these satellites shape the ring system, affecting its structure and stability over time. The modeling predicts significant material loss within the ring system, primarily due to gravitational interaction with the satellites. The complex dance between moons and rings is a key aspect of the Uranus system. The dynamic exclusion zones created by the satellites and the influence of these zones on the material distribution of the rings are crucial to understanding the structure and the evolution of the rings. The study also examines the role of satellite-to-satellite interactions in the evolution of the system, especially past resonances between satellites such as Ariel and Umbriel, and their impact on the orbits and geology of satellites, especially Miranda. But the mysteries surrounding this planet don't end there. You've probably heard of the aurora borealis. Well, the latest discovery concerns the auroras of Uranus, which also has them. However, its auroras, unlike Earth's, occur in the infrared spectrum. Using the Keck 2 telescope, astronomers observed enhanced emissions of trihydrogen cation in the planet's atmosphere. This is a groundbreaking discovery that sheds light on the unique magnetic field and dynamics of Uranus's atmosphere. Uranus's magnetic field, which is significantly deflected from the planet's axis of rotation, creates a unique coupling of the magnetosphere, ionosphere, and thermosphere. The detection of these infrared auroras is crucial because it opens up a new window into these processes, previously elusive due to the lack of such detections on Uranus. Comparing the polar auroras of Uranus with those of Jupiter and Saturn reveals their different characteristics. Unlike Jupiter, where the H3+ emissions have short lifetimes that smooth out the variability of the UV emission, the brightest infrared emissions of Uranus do not necessarily coincide with the brightest UV emissions of the other planets. This unique aspect of Uranus's polar lights provides valuable information for exoplanet studies, especially for the worlds of warm ice giants. The study delves deeper into the unusual heat spots on Uranus, observed near the latitudes of the UV northern lights. These spots, analyzed for temperature, column density, and total emission, suggest that the enhancement is not caused by temperature, but rather by increased ionization, probably due to polar aurora activity. Polar lights play a significant role in heating the atmosphere, and on Uranus, the increased H3+ emissions associated with these auroras suggest their involvement in atmospheric processes. By studying such unique things, we gain a deeper understanding of similar processes in different planetary environments, enriching our knowledge of how auroras shape planetary atmospheres, affecting not only thermal properties, but also the overall dynamics of the ionosphere and magnetosphere. In the quest to unravel the mysteries of our solar system, the ice giants Uranus and Neptune are distant enigmas beckoning closer exploration. Recent research, including a fresh analysis of Voyager images, has revealed that the two planets actually have similar shades of greenish-blue color, fundamentally changing our long-held beliefs. Uranus and Neptune share many common characteristics. They're roughly the same size, have the same mass, and are surrounded by deep atmospheres of comparable materials. Nevertheless, it was long thought that their appearance was quite different. This misconception has now been corrected. Both planets are shown in their true colors, largely influenced by the methane layer in their atmospheres. The need for a dedicated mission to Uranus has never been greater. Such a mission would not only deepen our understanding of the planet itself, but also provide a comparative view of Neptune and other similar icy giants. The mission's potential goals range from studying the unique magnetic field and complex ring system to investigating atmospheric dynamics and internal structure. In an important achievement for planetary exploration, the Uranus Orbiter and Probe mission has been elevated to the highest priority for NASA flagship mission within the 2023-2032 Planetary Science Decadal Survey. Future launch windows are available between 2030 and 2034. Key science goals will include a detailed analysis of the unusual tilt of Uranus's axis and its effect on the planet's climate and weather patterns. The mission can also study the intriguing phenomena of infrared auroras and their role in heating the atmosphere, providing a comparative study with other planets. Studying Uranus and Neptune will also provide valuable information about planetary evolution and dynamics. Understanding why Uranus appears slightly whiter, perhaps due to its more stagnant atmosphere, allowing methane haze to accumulate, can tell us a lot about atmospheric processes on the ice giants. As we await a future mission to Uranus, we stand on the threshold of discoveries that could redefine our understanding of the outer solar system. Exploring this distant ice giant will not only unravel its mysteries, but will also expand our knowledge of planetology as a whole, shedding light on the complex picture of our cosmic home.